Okay, hello everyone. Welcome to this session. Let me share my screen. I will get started.
Excuse me, ma'am.
Yeah, yes, tell me.
Ma'am, what will be the weightage week-wise?
The weightage of last 4 weeks will be 60%, and the first 8 weeks will be 40% roughly.
So there will be questions of
And
the
this is in
initial
terms
8
of
weeks
marks
also.
and number of
Yes.
questions, the weightage, like
Roughly both for marks as well as
okay.
number of questions.
So, ma'am, how many number of questions will be there in end semester? Will it be same or the more questions will be added there?
Number of questions, I'll have to exactly check and tell you, but this one will be 1.5 hours, correct?
Yeah.
Yeah, so number of questions will be slightly more than what you had in quiz 1 and 2.
Madam, I had one point to just raise.
Yeah,
On the
tell me,
same
Asma.
data, a number of questions are being asked on the same data, and if we make a silly mistake on one of them, we are losing marks for all of them. It happened with me for in quiz 1 and quiz 2. So like that, on the same data, number of questions on the same data, will we be having that way? And is it possible that some kind of a change in that would be there?
Actually, there wouldn't be much of it. So, but sometimes, you know what happens? There is a question, and that has, that you can break the solution, you can break in two parts. So, it has been done for you, keeping you all in mind, that we put that as, sub parts.
Yes, ma'am.
Sub
I
question
know
one and
the
sub question.
concepts are we actually understand them very clearly, but we don't, for myself, I'm speaking, I really don't get the same, I make some silly mistakes are happening, and usually they're happening in questions which are all linked together. So that was
Yeah,
one
I
issue.
understand. Yeah, so there wouldn't be much of it, but sometimes, it is inevitable. So actually breaking them into subparts is beneficial for you all, because what if you have done, two parts correctly and third part incorrectly? So if you put that as one question only, then you lose all the marks. But if you put that question in three subparts, in the form of three sub questions, then you at least get marks for the first two sub questions. So that's why you might find some questions like that. Please note that this is in your interest only, right? So if you break a question into subparts, it's actually beneficial, right? Because if the question is,
yes, ma'am, I get it actually.
I understand your point as well, but I don't think you would face such a problem, that silly mistake. Of course, you have to be careful. Well, we can't guarantee that, right? But yeah, sorry.
No, the same thing happened when I was doing in quiz 1. There was one on nearest neighbors. There were 3 of them, and we just didn't give the initial probability, and that way we lost all 9 marks.
Yeah, imagine we didn't have subparts to that. You would have, I mean, if you have done first subpart correctly, then at least you get some marks, isn't it?
Yes, madam. Yes, madam.
Anyway, yeah. So I hope you can see my screen. Can somebody please confirm?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Madam, this is not being live streamed on YouTube?
It is actually. It isn't. It is
No,
being,
actually,
right?
they are asking in the chat.
The YouTube link probably might not be there in the calendar. Yeah, YouTube link is not in the calendar, but it is
Can
being
you
live
share the
streamed in
YouTube
the.
link just now?
Right
on CS
now,
channel, it is not to be seen actually. On YouTube CS channel.
Yeah. So you should get it after the session.
Okay.
Will that be okay? Yeah. Okay. So I'm actually recording as well, just in case.
Ma'am, the difficulty level would vary, or it will be same as of quizzes?
Similar to quizzes.
Okay.
Yeah. Anyway, I'm going to scribble here. So we're going to start with week 9. And as we know, perceptron and logistic regression are there in this week. So perceptron is a very straightforward, algorithm, but it also has one assumption that the data should be linearly separable, right? So that's one thing. We'll talk about linear separability in a while in a little more detail. So let's quickly write the steps of the algorithm. And what we do in perceptron is, until convergence, what we do, and we'll talk about what convergence is here. So what we do is we pick a data point. Again, we'll talk about which data point we'll pick from the data set. Okay,
we pick one at a time from the given data.
We pick one at a time. So this is something which you should note. We pick one at a time. Okay, we do not apply the weight on the entire data set in one go. This is what I want you to know. So we initialize some weight vector. If there are,
one thing here, ma'am, see this W0 initialization, can it be given in question that a particular weight vector, which is a non-zero weight vector, to be initialized?
We can actually start with a with some random, arbitrarily
any
initialized weight
so
vector. We can do that.
Okay. It is not a zero vector in all, I mean, by default.
So in our lectures, actually, we are sticking to this assumption that we are starting off with initial weight vector to be 0, and there's a reason for that. This is actually beneficial in proving the convergence of perceptron. Okay, so that is beneficial there, but in practice, you can start with any arbitrary weight vector. For questions, if you are concerned about, you should use 0 weight vector. It should actually be mentioned, but just in case it is not mentioned, you should take initial weight vector to be 0 only. Is that clear?
Yeah, I just wanted, I was just thinking whether in quiz questions, some non-zero weight vector could be given as a initialization. That's all I wanted to ask.
In quiz questions, you should take weight vector to be 0. Just in case, you can take any vector that should be explicitly mentioned in the question. Okay. So for final exam, take it to be a 0 vector. Anyway, getting back to the perceptron algorithm, you pick one data point, and on that data point, you check whether the sign of W transpose X, so Xi, if it is equal to Yi. So Yi
+1 or -1
can be +1 or -1. In perceptron, we take it to be plus and minus. So if the sign matches, you do nothing. If the sign doesn't match, what do you do?
Ma'am,
you apply an update
one
rule,
thing just here, if in the initial, if it is 0, so we take the sign of 0 as +1.
So, what is 0?
I mean,
yes, sign of 0 is +1, correct.
Okay.
Yeah. So this is the update rule that we apply. Wt plus 1 is equal to Wt plus Xi Yi, simply. So we start with the weight vector 0, and then we pick one data point. In the order in which we pick the data point should be given in the question. So in practice, we follow some sequence. So if you see any implementation of perceptron, some sequence is followed. In any question that is given to you, again, the sequence will be given to you. For example, you would be given that you should take the data points in this sequence. Let's say 4 data points are there. This sequence, or maybe x4, x3, x2, x1, some sequence will be given. So you will apply this weight vector on each of these data points one by one. In case the sign matches with Yi, you do nothing. And in case the sign doesn't match, you update the weight vector. So, which means you start with W0 and you apply W0 on X1. If the sign matches, you don't do anything. You move with the same copy of W towards X2. Just in case it doesn't match, you update it to a new weight vector by applying this update formula, and let's say you get W1, and you move to the next data point with W1. Let's say there is a mistake here as well. Once again, you will update it to W2, let's say, and you will move to the next data point with W2. And again, you will once again check. So what do we mean by convergence here? When you, let's say, have followed an entire pass and there hadn't been any mistake, that's what we mean by convergence, which means all the data points are being correctly predicted by the current copy of W. So the point to note here is that we keep a running copy of W in every pass, right? Any doubt till this point? Some
thing,
people had
madam.
this doubt. Yeah.
Yes.
One thing. So suppose after first pass, we came to a particular weight vector. Then again, we are checking with every data point. So in the second pass also, there is some misclassification for
Okay.
some other data point. So suppose in this case, there are 4 data points. So in 4 passes, we are having 4 different misclassification. So
Okay.
when do we know that convergence has happened?
Yeah, that's what. So that's what I said. If the mistake is happening, you will keep updating it, and then you. So what do you mean? What do you mean by pass? So I by pass I mean
Bypass
this
means
entire
going,
thing, right? A pop.
predicting all the data points with the one weight vector.
Correct. So let's say there was a mistake. So I think what you're saying is there was a mistake here, you updated it. There was a mistake here, you updated, mistake and updated, and then you go back here, right? And then you check once again. If there is no mistake here, no mistake here, no mistake in each of these data points in the given pass, then you stop.
Correct. So we need to keep on doing this till there is a particular pass in which there are no mistakes.
Correct. Yes.
So, but if that hypothetically, if that doesn't happen, say suppose 4 data points are there, and in 4 passes, every time some mistake happens. Hypothetically, I'm saying, then how can we conclude whether it is converging or not?
Every time. So you're saying that you are running
Yes.
different passes, and every time some mistake is
Hypothetically.
happening. Okay. So so that will not happen hypothetically, because we have perceptron convergence algorithm, right? Convergence proof, right? Did you
Yes,
go through that proof?
maximum number of mistakes.
Right. So convergence proof is actually based on the fact that there are going to be some finite number of
R
mistakes.
square by
Okay, we have a limit.
margin square.
Correct. R square by gamma square, which is called radius margin bound. So if you are saying that hypothetically the mistakes keep happening, you will stop at some point.
At most, if L is equal to R square by gamma square, then in that particular iteration, it will definitely converge.
Correct.
Understood.
So this is actually the upper bound. You will actually converge much before than that.
Yeah, please give such question that we don't have.
Yeah.
To do that
So
much.
in exam, the kind of question that you will get, it won't happen that it won't converge very soon. Okay.
Hello.
So worry about it. Yeah.
Ma'am, this might be a silly doubt. Let's say we keep on iterating over x1, x2, x3, and somehow we get a mistake at x4. So then after updating x4, then we again start from x1. Like every time we update W, we
You
keep
go to the next one.
So let's say there are only x4. So we start from x1, or what do we do?
You made an update here, is it?
Yes, ma'am, in the last one.
You made an update here. After that, you move to the next data point.
So that is we started again.
Start
in the
again.
same sequence of x1
In
to
the same
x4.
sequence. Exactly. In the same
Okay.
sequence.
We keep on doing in the same sequence, not again
Yes.
and again and again. Okay, right.
In the same sequence. Yeah.
Okay.
Ma'am, I have a question.
Yeah. Go on.
When I did all these assignments, when I updated the weight vector, actually I started from the first data point. It is okay to do like that?
You started from the first
If
data
the
point.
sequence is not given,
Yeah.
then we can start
Correct.
from x1.
Correct. If the sequence is not given, you will start somewhere, right? So the obvious choice is to start from the beginning. So that is fine. Okay. So actually,
okay.
if we know that there is going to be only one mistake in the data set, let's say there are 4 data points, and we know that there will only be one mistake. In that question, if we do not mention the sequence, it doesn't matter, isn't it?
Yes, ma'am.
If you know that there's only one mistake that is going to happen, we will update the weight vector based on this, and we are done, right? But let's say in a data set there are more than one mistake. Now here we don't know which one to update first, because you should actually practice this. Take up some example. So when we follow a particular sequence, we might get a different number of updates. And it may happen that when we follow a different sequence of data points, then we may get a different number of mistakes. So that may happen. That is why it is important that for having a common result, we should know what is the sequence that we are going to follow. Hence, in the question, the sequence will be mentioned.
Yes, ma'am. I just did in the given order, and the data points given in the order. When the weight vector is updated, I start again from the first data point in the order. So, is it okay to do that?
Yeah, if the weight vector is if the sequence is not given, yes, you will start from the first data point. Yes.
Okay.
Yeah, but in each subsequent iteration, we need to follow the same sequence which we followed in the previous iteration.
Correct.
Yeah,
We need
yeah,
to follow the same sequence. So I think I should do one example here so that you understand where is that question. That question might be somewhere. Okay. So this question, is this clear to everyone? Do you want me to follow this? Because this will
Yes.
clarify.
Yeah, this is like the one we were discussing right
please do it.
Let me see if I can have it here. I don't know. No, anyway, so let's see it here only. So this is the data set.
If you can do Windows Shift S, then it will copy. Windows Shift S.
No, I was trying to take a screenshot.
Yeah,
actually.
so Windows Shift S, window button.
Screenshot is fine. Screenshot I can take, but somehow some issue. I need to restart my system. Anyway, never mind. So it's okay. So this is the data that we have. Let me write this down. So this question will clarify your doubts. So this is what is given to us. Right. So in this question, the sequence is given to be x4, x3, x2, x1, right? And the labels are +1 for this one and -1 for the rest, right? We are not given the initial weight vector. We'll be taking that to be a 0 vector, right? So you decide to cycle through the points in this order repeatedly until you find a linear separator. So the question asks how many mistakes we made and what is the linear separator that we got, right? So we take W0 to be 0, 0. The order is x4, x3, x2, x1, right? So we apply this W0 to x4. So W transpose x4 will give us what? 0, 0, 0. That is going to give us 0, right? And what is the rule? If it is greater than or equal to 0, we predict +1 class. If it is less than 0, we predict negative class, right? So the class predicted will be +1, which is not matching. So it's a mistake. Now, when a mistake happens, we update the weight vector. I'll not write the subscript. So update the weight vector. W1 is equal to W0 plus X into Y, right? What is W here? W is 0, 0. What is XY? X is 0 minus 1. So this is where the mistake happened. And this Y is the actual Y. Please note this. This Y is the actual Y. So X is 0 minus 1 and Y is minus 1, right? So this is 0, 0 plus 0, 1. And this gives us weight vector to be 0, 1. Now with this weight vector, we move to the next data point, which means this is W1, right? So W1 transpose X3 is what we will find out.
Now, ma'am, here what I am doing, I am starting again with X4.
No. That's what I told you. You have to keep a running copy and you have to reverse through all the data points in the given order. Is that clear? You don't go back.
So breaking and starting again, it will not work. I follow all questions like this. I got the answers for all questions.
That's why I'm highlighting this. Few students had this doubt in this course also. So you see, actually, your algorithm may converge even in following what you are doing, but then probably the number of mistakes will be different from what we will get in this particular case, right? So that's why we have to stick to this particular order. And you take any implementation of Perceptron, internally there'll be some order that they will be following. And you can understand it is important to follow some order, isn't it?
Yes.
So you, with this weight vector, you move on to x3, and that is what? 0, 1 into x3. So what do you get? 1, which is greater than or equal to 0. So you get a +1, and there is a +1. So there is a match. There's no mistake. So we move to x2 with the same copy of w, which is w1 here, right? We move to x2 with the same copy w1. So we compute w1 transpose x2 with this weight vector and this x2. What do you get? 0 plus 0, right? You get 0 here, and which is going to give you +1 class, and the given class is -1, which is a mistake. So there's a mistake that happens here. So you will update w2, which is w2 is equal to w1 plus xy. What is, so w1 is, what is w1 here? 0, 1, right? And what is x? X is -1, 0. And what is y? The actual y is -1, right? So you get 0, 1 plus 1, 0, and you get 1, 1, right? This is your w2. Now you move to x1 with w2, right? With w2 you move to x1. So I hope you can see this. So w2 you will use for x1, right? And that will give you, so this is 1, 1, and this is -1, 1. What do you get? -1, -1, which is -2. So this will give you -1 class, right? And the given class is -1, which is matching. So there is no mistake here. Now what we do is we go back here after x4. You go back to x1, and we'll see whether it works. So with w2 we go to so x4 we have done, right? So sorry, what was the order? X4, x3. Sorry, that is not the correct order. So x4, x3, x2, x1 order we followed, and after x1 we go back to x4, right? With this w2 copy we go to x4. W2 copy is this 1, 1, right? 1, 1, and then okay, this is the order. Yeah. So 1, 1. We will check for x4, right? When you check 1, 1 with 0, 1, what do you get?
Now
W
all
transpose
predictions
x4.
are coming correctly, madam.
Right. So 0, -1. So the given class will be -1, which is matching. When you check 1, 1 on the next data point, which is x3, that is 1, right? So +1, the class will be correct. And if you check 1, 1 on this data point, what you get? -1 you get. So predicted class will be -1. When you check 1, 1 on x1, you get -2, and the predicted class will be -2. So you check the entire pass, and you saw that this particular data w weight vector is working fine with all the data points. So you stop there. So the result will be 1, 1. And how many mistakes did it make? It made 2 mistakes. That's the answer. Any doubt here?
If we are
No,
asked
ma'am.
for number of iterations, what will be the answer?
Iterations is actually something confusing. So actually iterations is equal to number of passes, and that is also sometimes referred to as epochs, right? Epochs means how many times you pass through the entire data set. So you won't get a question like that, because we are going to follow data points one by one. So but in case there's a question on iterations, then we made 2 iterations over this data, isn't it?
Yes.
In the first iteration we got 2 mistakes. In the second iteration we didn't get in any mistake. So if you want to ask about iterations, that's what it is. Okay.
Yeah.
Iterations is same as epochs. Sometimes in gradient descent we refer to the number of passes through the entire data set to be epochs. Okay. All right. So another thing to note here in this week is the number of maximum number of mistakes that can be there, and that comes from the proof of convergence of perceptron algorithm. And there we make 3 assumptions. The first assumption is the linear separability with gamma margin, right? Which means there should not be any data point on the decision boundary itself. There should be a gamma margin on both sides, right? That's what this assumption is. And second is the radius assumption that we make. It's actually not an assumption. This is actually a help full simplification that makes the proof simpler. Radius assumption. So the data points are given, right?
So radius assumption is kind of a given, because given
It's-
all
yeah.
the data points, definitely there will be some
Correct.
R in which it will be within that sphere.
Correct. So I want to add one more point here, just in case the R is not given. Let's say you have some question where you require R. Can somebody tell me how would you find that out? What is R?
We will
Distance of maximum
calculate the length of all
data
points.
point.
Length of
Correct.
largest
So
vector.
length of each data point you can compute from the given data points, right? So whatever is the maximum length, that is going to be your R, right? So again, so that's why I said it is not an assumption, it's just a simplification. And the third one is, we assume that the final, let's say W star, we assume that the final weight vector length is equal to 1. So okay, so it is not going to change anything. It will just change the value of gamma, but gamma margin should be there. That is the only assumption. So it is not going to affect anything. So in the proof,
No, this W star, norm of W star equal to 1, it helped in that equation of WT plus 1, norm of W star equal to L gamma, and there W star norm became 1.
correct.
So that WT plus 1 equal to L gamma.
Right. So that's why I said it's a simplification, right? It helps in the proof, correct? It helps in the proof. So what I'm
Yes.
saying is, it is not going to alter the way perceptron works, right? So that is why we can safely assume this. So there won't be any issue if you assume this. So in the proof, what we do basically, we keep track of how WL plus 1 varies with respect to WL, right? So we know this update rule, right? Wn plus 1 is equal to WL plus X into Y. This update rule we know. So what we are doing is, if you take square on both sides, you get, and you expand. That's not difficult, so you can look that up. So you are simply squaring both sides, and what you get is this L plus 1 R square. So this is something you may want to note. Sorry, less than equal to.
Yeah, here L plus 1 we are taking, but in the lecture video, sir had taken LR square.
Yeah, that should actually be L plus 1.
Ma'am,
that should be L plus
also
1.
for this question, also this L plus 1, I solved it using L only, and now all the answers are correct. Now,
No,
what?
not
Right.
correct.
So which
In the
question did
sense,
you answer? So it depends on what question you answered. If you answered this, L is less than equal to R square by gamma square, which is radius margin. So this won't be affected. So as I will show you, this won't be affected. This formula is
no, ma'am. Particularly if with the thing inequality you just now wrote, that question 1 in graded assignment is basis this inequality.
Yeah, correct.
Whereas if we take only LR square, then we only get one
One answer.
One answer.
Yeah,
That is
so
where my question was. So from where we are taking this L plus 1 R square?
from where we are taking, is it?
No, I mean, in the sense, in lecture video, sir had taken LR square. And
yeah,
here,
that's a mistake. So there should be L plus 1 there, is what I'm telling you. So if you see this, yeah, that's a mistake. So if you see this, when L minus 1 is there,
Excuse me, ma'am.
yeah.
Ma'am, this similar question I asked again, and the same was marked back to you, because after your last lecture in the live class, there was a discourse by another. There was a discourse. What you say? I mean, something on discourse, and there again they didn't add +1, and I raised a query and it was marked probably back to you, or I think I was asked to mark to you. So this
Who
is
is
still a
this?
confusion. I think by Karthik, he had asked me to mark
No,
that.
there's no confusion. So let me finish this, and then you let me know if there is still any confusion. Okay.
Yeah. Okay.
Okay. So if you stare at this particular equation, I hope you can see my cursor. So when L minus 1 is there, then you have 2 R square here. Yes or no?
Yes.
Correct.
Yeah.
Now,
yes.
if you keep going on in this fashion, when you have L minus L here, you would have L plus 1 R square here. Yes or no?
Yes, ma'am.
Correct. So L minus L means 0. Correct. So when L minus L here is there, then you will have L plus 1 R square over here. But here we have written L, which is incorrect. So you replace L by L plus 1 here. That's what we are doing here. L plus 1 R square is correct. Is this clear? Any doubts so far?
Ma'am, then number of mistake will be L or L plus 1?
L is the number of mistakes.
So if this is the case, then how are...
So you can actually rewrite this as WL norm WL square is less than or equal to L R square, right? You can write it like this. Yeah?
Yes.
Yes.
So this is what we got as the first equation, right? Now, the second thing is, we want to see how WL plus 1 varies with respect to the final weight vector, which is able to separate all the data points. We want to see how the weight vector at any point of time behaves with respect to W star. So what we do is we take the dot product of them, or you can say you take the transpose of them. And then when you expand this, WL plus 1 is equal to WL plus XY transpose W star, right? This is what you get. Now, when you further expand it, what you get is WL plus 1, norm WL plus 1 square is greater than or equal to L plus 1 square gamma square, right? Once again, there is a mismatch here. In the lectures, it is
ma'am, now it is clear.
L. I hope this is clear once again.
Yes, ma'am.
Yeah, ma'am. I think both left and right should be synchronized. Here, there's a mismatch of one level.
Yeah, here this conversion
Okay, got it.
has a problem. You just put L plus 1 here. Okay. Now, once again, you can rewrite this as WL norm WL square is greater than or equal to L square gamma square. So what I'm saying is this and this are the final ones. Now you can use them, and when you use these two, you get this, right? So the final number of mistakes, the upper bound on the number of mistakes remains the same. That's why probably you got the correct result, because you would have used this, right?
Now, the left hand side is WL or WL1? What is this?
This one, WL. Sorry, this is very badly written. WL. Yeah.
Ma'am, I have one doubt. Where can I find this equation apart from that slides? Is there any book which also follows same notation and equations? No, because in the reference book section, the books they have mentioned, I can't find these equations.
Okay, so we'll have to look that up. You want the same notations and everything, of course.
Kind of a derivation and equations. Any book which follows in detail, like how sir teaches like that. I have to cross check that.
So I don't think there will be one book that will have all the content that sir has taught. So it will be from different sources, but we can look that up and share as much as we can find which is matching with sir's content. We can see that.
Thank you.
Ma'am, what will be the Cauchy-Schwarz inequality then? Will it be
that will remain the same? There's no problem there.
So WL plus 1 squared will be sandwiched between L square gamma square and LR square, or L plus 1 R square?
WL plus 1. L plus 1 only. Where is that? That will remain the same. WL plus 1, this thing, right?
Yeah.
So here it will be L plus 1 whole square gamma square.
Here there is no issue. It will still remain L plus 1 only, right?
All right.
Yeah.
Got it. Thank you.
Basically, if it's L plus 1, the right should be L plus 1, L plus 2, then right also L plus 2. And I mean, whatever stage.
Yeah, that's all. That's all. All right. So, any other doubt that you have in this week? Any other questions that you have? Okay. So, shall we move on to the next week then?
Something on logistic, you can say, ma'am.
Okay, logistic, correct. Yeah, let me cover that up also. So let me do one thing. Let me follow the slide. So, what is the drawback of Perceptron? Can somebody tell me? What is the drawback of Perceptron?
Too simplistic. Yes,
Probability we don't get here.
Outliers.
Linearly separable.
Linearly separable, right? Linearly separable. Yeah. If your data is not linearly separable, then what will happen if you apply Perceptron on that?
There will be misclassifications.
It keeps oscillating.
It will keep oscillating, right? It will not converge, correct, right? It will not converge. So in practice, the kind of data that we get is never this perfect that it will be linearly separable.
Basically, in trying to improve one, it may spoil 10 more. I mean, something.
Correct. Right. That's true. So we need an algorithm that is able to handle a little bit here and there data points which are on the wrong side as well. That's why we want to look for another algorithm. So how do we do it? So let's talk about that. So in Perceptron, we have you can write the output of Perceptron in the form of probabilities, which can be either 0 or 1, which means probability of y is equal to 1 given x is equal to 1 if W transpose x is greater than or equal to 0. It is perfectly 1. It will not less than 1. It will nowhere between 0 and 1. It is either 1. If when is it 1? When W transpose x is greater than or equal to 0. Otherwise, it is 0. So this is a very rigid model, isn't it? So what if we get probabilities somewhere between 0 and 1, depending on the placement of the data point? For example, if you look at this particular figure, you see that there is a negative data point here, which is on the incorrect side. So we should be able to assign a very low probability of being positive to this data point. Yes or no? Right? This data point is in the wrong
each
side.
data point will have some probability for each side, and
right.
higher probability for the side it actually belongs to.
Right. So every data point will have some probability of being positive and some probability of being negative. Now this data point is in the incorrect side of the decision boundary. So this data point should have a very low probability of being positive, right? So that our model should be able to give us. So what we do is so that's why we go for something like logistic regression. So what it does is
low probability of being positive or high probability of being positive and low probability of being negative?
For an outlier, it will be low probability of
so this data point is on the right side of this decision boundary. Correct. So this will have a high probability of being positive, but a low probability of being negative. Right?
Yeah, correct.
Yeah, correct. Similarly, this data point, if you see, this has a high probability of being positive, but a low probability of high probability of being negative and low probability of being positive. Right? Yeah. So this probability we should be able to get. Now, how can we get the probability? If you see, if a data point is closer to this decision boundary, the probability should be low, right? Because we are not sure about the decision, isn't it? But if the data point is much farther away from this decision boundary, then the probability should be high, right? If there is a data point over here where my cursor is, the probability of being positive should be high, isn't it? Because it is much farther away from the decision boundary. On the other hand, if there is a data point which is very close to decision boundary here at my cursor, then the probability should be low, which means the distance from the decision boundary should be proportional to the probability, right? And how do we get the distance from the decision boundary? That is the W transpose X value, right? So what I'm saying is, if this is the decision boundary, here W transpose X is equal to 0, right? This is the boundary where W transpose X maybe, let's say, is equal to 1. This is a boundary where W transpose X is equal to 100. So if there is a data point here, and if there is a data point here, since this data point is closer to the decision boundary, it has less probability of being positive. Whereas this data point is farther away, so it has high probability of being positive. So which means this W transpose X value is actually proportional to the probability values, right? But probability we know lies between 0 and 1, right? So that's why we use what is called a link function, which is a sigmoid function or logistic function. That is what we use in logistic regression, which converts a given value to a value between 0 and 1. So if, let's say, this is the function, it will be 1 plus e to the minus e. So if any W transpose X value we get, we just apply this function and we get a value between 0 and 1, right? So that's how we get the probabilities. So given any kind of data type, given any kind of data set, we can use logistic regression, and we'll be getting the probabilities for each data point to belong to either positive class or negative class, and accordingly we can decide what class to be assigned to that. If it is more than 0.5, we assign positive class. If it is less than 0.5, we assign negative class, right? Now, another point to note is, how do we get the weight vector here, right? So the weight vector we get using maximum likelihood estimation, as you might know. So if you see this diagram, actually any decision boundary will work, right? So you will get some probabilities. There's no oscillation that will happen, unlike perceptron. You take any decision boundary, you will get some probability values, right? But what is our motive here? Our motive is to maximize the probabilities. Our motive is to get the probability such that the resultant probability that we get, for example, for this data point, what probabilities we get for being positive and negative. For this data point, what probabilities we get for being positive and negative. So basically, Bernoulli maximum likelihood estimation you can apply, because every data point has some probability of being positive, some probability of being negative, right? So it's a two case problem. So that's why we multiply all the probabilities. So when yi is equal to 1, what will be the probability? G of W transpose Xi. When yi is equal to 0, then this probability will hold. So we can compute the maximum likelihood estimation, and you can get the value of W. So if you expand all this, you get the W. And our motive is to maximize this, right? So we can apply something like gradient descent or gradient ascent in this case, right? If you want to minimize something, then you apply gradient descent. If you want to maximize something, you will apply gradient ascent, where instead of negative, you will have a positive here, right? So that's how you get the weights in logistic regression. Yeah, that's about it. Any other doubt here? So,
is logistic regression also an iterative process like perceptron, where we keep on iterating until there is no noise in the data?
Okay, if I ask you, if is linear regression iterative?
Not exactly.
Okay, if you apply gradient descent on linear regression to get the weights, right? You understand that?
Yeah.
Same way, similar will be how logistic regression is
But
functioning,
gradient
right?
descent is an iterative process.
Yes.
The same way, getting weights for logistic regression is also iterative process, right?
Okay.
It's just that whatever values you will get, so ultimately you get some W, right? After following this gradient descent, which is actually iterative, you get some value of W, right? You apply this W to any given data point. Whatever you get, you apply the sigmoid to it, and hence you get the values between 0 and 1. And based on that, you decide whether to, declare +1 or -1. Is that clear?
Sure. So
we can actually decide.
Sure. Please go ahead.
I was just saying that generally we keep 0.5 to be the separator, but it is also possible to change it. So generally what we do is, if the probability is greater than 0.5, you declare the class to be positive, else negative. But it is possible to change this. This is possible to change. This is called threshold. Well, go on, please.
Yeah, thank you. So I was asking that in the exam, can we expect some kind of questions where the number of iterations will be defined, like what will be the value of W? Is that sort of the expectation?
Computing W, is it? No, computing W. No, you may not get the question on that. Yeah.
All right.
Because that would require a lot of iterations, right?
That's what I was.
Yeah. You won't get any question on that,
okay,
at least in the exam. But still, you should know the process. That's all.
Yes.
Hello, ma'am.
So, like you said,
threshold. Any
Sorry, I couldn't
criteria?
get you.
Any criteria to select threshold value?
There is actually AUC ROC curve, right? So, okay, you will do that in MLP. There are criteria to decide on the threshold. Yeah.
Okay.
So actually, when you change the threshold, then precision and recall change. So wherever precision and recall are the best values, that's where you stop.
Normally,
right?
the threshold sticks to the distribution of the classes. Say the 0 class is 60% and one class is 40%, the threshold comes around that level only, like 56, 57.
No and yes.
Okay.
I'm not sure I understood you completely.
I mean,
So,
there's an
so
imbalanced data set, say, which has 60% of one class and 40% of another class. These thresholds
yeah,
seem,
it will actually be dependent on that.
yeah.
But it will also be dependent on the placement of the data points, plus and minus, right? How much intermix is there? It will also be dependent on that, because you know why? The moment you shift the threshold to right hand side, something that was earlier being predicted as positive, now that will be predicted as negative, isn't it?
Yeah, the
Similarly,
recall
when
and
you shift it here, so accordingly precision and recall will change. Well,
yeah,
we should
exactly.
not discuss this because you will do it later on.
Okay.
But since you asked, based on
Yeah.
these values,
Ma'am,
we
there's
decide
this
the
question
threshold. Okay?
8 in graded
So, ma'am,
Just
if
a
the
assignment
value is
9.
0.8,
Question 8 in graded assignment 9, in which there's this one straight line for decision boundary for logistic regression curve.
Mhm.
So suppose
Yeah.
if a similar question graph is given and instead of one straight line, there are 2, 3 straight lines given.
Okay.
So then
Okay.
which one to do, and each of them is like separating the data set.
Okay. It depends on the data, right? And you may not be able to visually tell
Like the
like
question
this,
was asking which
like
is the
that this is
decision
the
boundary.
decision boundary.
Yes.
You may not get this question because you need to solve, given the data points, you need to see what is the best value of W, and accordingly you will get a linear separator, right?
Okay.
Just
Understood.
visually looking at the data, you may not be able to say that, okay, this is the
Okay.
best
Thank
one.
you.
You won't get such questions, okay?
so
No,
ma'am,
ma'am.
if the
It's like
value
Actually,
you're
is
trying to
point
guess the
there was
question,
this
isn't it?
question, and I just
Anyway,
came across like there 2, 3 lines are given.
yeah, that was just to reinforce that the decision boundary of logistic regression is linear, because some people have this confusion that it is not linear, it is non-linear, because probably we are using sigmoid function. But I hope you all are clear with the fact that sigmoid function is just transforming a linear value to another linear
Correct.
value, right? I mean, it's not that our
Okay,
decision
ma'am.
boundary is becoming non-linear after applying sigmoid, right? Okay,
hello
somebody had a
ma'am.
question. Yeah, go on.
Yeah, so if the value is 0.8, then we can say that label can be 1 with probability 0.8. We can't be sure that the label will be plus 1 only, right?
Yeah, if it is
Greater
0.8,
than equal to.
we will say the label will be data will be positive with probability 0.8 and negative with 0.2, right?
Point, yeah.
And hence we will be assigning a positive class to that data point, right?
Is that for sure that we are
Assuming the
assigning?
threshold to be 0.5. Yeah, generally assuming the threshold to be 0.5, we will assign that data point to be positive. I mean, why would you
Okay.
want to assign a label to a data point which has a
Low probability.
negative probability of 0.2, right?
Hmm.
There's more probability of being positive, so you will assign that data point as positive only, right?
So threshold is in a sense, it's something like a margin.
Yes, not margin, separator sort of. I mean,
Okay.
yeah, it's not margin.
Just this in this context, just the error in the model. Can I correlate that to with the accuracy of the model?
Error is different, accuracy is different, isn't it? What is accuracy? What is accuracy? We actually haven't studied in this course. Maybe you know from before. So how do you connect these two? Of course, they are connected, but they're not equal, right? What is accuracy?
The
Accuracy.
actual versus predicted is
Number of points
So
predicted.
correctly predicted divided by total predicted into 100, right? I mean, yeah, right? Correctly predicted divided by total data points. That's your accuracy. And what is error here?
Error here is the number of point that I
They are proportional, right?
misclassified.
So let's say you're using
Misclassified.
0-1 loss here. It's a classification problem. You can use 0-1, right? So of course, it depends on which loss function you're using. Like you might know from week 12 that there are several loss functions you can use. But in general, in classification, we are interested in increasing the number of correctly predicted data points, right? So error here is, I mean, if the data point is matching, the label is matching, you put a 0. If the label is not matching, you put a 1. So error is actually opposite to accuracy, isn't it here?
Not
If
exactly.
no, if there are let's say out of 10, there are 8 correctly predicted, right? So how much will be accuracy?
0.8.
0.2, right?
minus error.
And if error, how much will be error? 8. Sorry, how much are correctly predicted?
8 out of 10, so
8.
80
8 are,
accuracy, 80%.
right? So they're opposite to each other, isn't it?
Okay. No, actually, all these things asking when I'm changing this threshold, as you say, the precision and recall value get changes. Will the accuracy is also impacted?
Definitely. Accuracy will also be impacted. But accuracy is not a good measure, actually. You would study later on. Accuracy is not a good measure. Let's not get into that. So, yeah, of course, that will be affected.
Okay.
Yeah. All right. So,
And this calculation of this logistic function value, that could be time consuming.
yes, that will be time consuming. That will take time. That's not a straightforward equation, as you see.
No, there was,
So you would not be
there
asked
was
to,
the
put
question
values in
related
that equation and
assignment,
compute.
so,
No. Not,
but then,
which
no,
one?
not that. One
No,
by
there
one,
was no
we had
question
to
on that.
calculate 1 by 1 plus e to the power minus z.
That much is fine, right? I mean, that much is fine. Finding what would your logistic function give you, that you can do, right? I mean, that's not going to take a lot of time.
And in the
So,
lectures,
but computing W type of questions wouldn't come, right?
From logistic regression, finding W? No.
Yeah. You do that by gradient update,
Yeah,
right?
gradient is, you cannot do that manually, right? You won't get that.
Okay, ma'am.
Okay, let's move on to week 10 then. Hi, Karthik.
Yeah, ma'am. Yeah.
Sure.
Sure. Is my voice audible?
Yes, Karthik.
Yeah.
Okay. 1 second, I'm sharing. Okay, so I just want you to confirm if it's visible.
Yes, SVM summary.
Okay, yeah. So we'll begin from where we left off. Next slide is also okay. Yeah. So far we have seen Perceptron, right? So we'll use that as a inboard to move to SVMs. So for linearly separable data with gamma margin, what we have seen is Perceptron gives us one possible separating hyperplane or separator, right? So strictly speaking, there are infinitely many possible linear classifiers, right? So all of these three classifiers that are shown in here are all valid linear classifiers, right? So the natural question is, Perceptron returns one of them. So is it the best, right? So is it the best possible linear classifier that we can come up with? And first of all, what do we mean by this notion of best, right? So the SVMs are all, the study or motivation of SVM is centered around this question of, given a set of data points, we again start with the linearly separable case. How can I find the best possible linear classifier, right? So that is the main motivation behind going through SVMs. So in order to understand SVMs properly, we need to understand margin quite well. So the idea of margin is something like this, right? So you have these two separating hyperplanes and you have some margin here. Now, this is the margin for one particular linear classifier. Now, there are some problems with this, right? So here the margin is small, right? So when I mean margin, I'm talking about the distance between these two dotted lines, right? Roughly, you can treat that as the margin now. It will become more precise as we go along. So small margins, they do not generalize well. Right? So as an example, what we have done is we have taken these two additional data points, right? So they are, think about them as green and red points, but from the training data set. Right? So while training, from the test data set. So while training, you don't have access to these white colored extra data points. So if you have a small margin, the problem is that you have a high chance of misclassifying examples from the test data set. This is what we typically mean when we say that the model doesn't generalize well, right? So on unseen data points, your model is not going to perform well if you have a small margin. So which means that if you have a larger margin, then notice that the same white colored data points are not correctly classified. So these two assume that they are from the green class and these two are from the red class. So we see that larger margins generalize better. So going back to our the earlier slide, we see that one notion of a best linear classifier is something which has a large margin, right? So that is what we are trying to do now. So the next step will be to compute the margin. Any questions? Okay, so the next step would be to compute the margin. So this idea of margin is kind of generic to any linear classifier, right? So not particularly the optimal classifier that we are looking for. Any linear classifier for which there is a weight vector W, it will have a margin associated with it. Okay, so there is a proper algorithm or procedure to find what this value is. So given a classifier, you look for the point that is closest to it, right? Let's say it's X star. Let's call that point X star. So what we do is we scale the weight vector such that X star, this point X star lies on the line W transpose X equal to 1. Okay, so if you remember in the lectures, this is what professor would have done, but in a slightly different way. I'm just presenting it in a different way here. Okay, so we are allowed to scale W because that doesn't change your decision boundary. Okay, so W, 2W, 3W, 1.5W, they're all the same. They all correspond to the same line. Okay, so you have the flexibility to scale the W. And when you do this, what happens is that the distance of this closest point from your line turns out to be 1 by norm of W. Okay, so this is what we say is the width of these two separating hyperplanes, right? So we say 2 by norm W is the width. What is shown here is half the width. So 2 by norm W is something you have to keep in mind. So this is what is called the geometric margin, right? So there are different notions of margin. There is something called functional margin, which we haven't really discussed. But this particular version of the margin is called the geometric margin, okay? So it kind of gives you the distance of the closest point to your classifier. All right, so once you have the margin fixed, what we see is that every point in a linearly separable data set should lie beyond the margin, right? So it should satisfy this inequality, which is W transpose Xi Ya should be greater than or equal to 1. Okay, for the green color data points, Ya will be 1. So this will just be W transpose Xi greater than or equal to 1. For the red color data points, Ya will be -1. Therefore, this W transpose Xi will also be negative. Ya will be -1. So they'll kind of cancel each other out, and you will still have W transpose Xy greater than or equal to 1. Okay, so this is the fundamental set of constraints in your SVM. N constraints for n data points. So moment you see that, you can now frame it as an optimization problem. What you're looking for is you have to maximize the margin. Margin, as I told you, is 1 by norm W or 2 by norm W. It doesn't really matter. So you have to maximize this margin subject to these constraints. Okay, so now Can someone tell me how I can reframe that objective function? Is there a way I can write it differently?
1 minus w transpose xi yi less than equal to 0.
Okay, that's the constraint, but how will you rewrite the objective function?
Minimize like
Minimize.
Okay, right. So you'll
Minimize.
W
turn this into
So,
minimize.
one just small clarification.
Yeah.
So, whenever in the question they ask for the margin, what is the thing that we should consider? As far as whenever I heard the term called margin, shall I consider this is 1 by norm W or 2 by norm W?
2 by, let's stick to 2 by norm W, but the idea is clear, right? The idea is more important. The idea is that
Idea is
margin,
clear.
yeah, okay, then fine. Then you have to, let's stick to 2 by norm W for the exam, okay?
The
So
2 by norm W will be like both sides of decision boundary.
Yeah,
correct?
so yeah, that is the width of this whole thing, right? Just the width of the distance between the
margin
two
is one side of the decision boundary or both sides of the decision boundary.
So see, this is kind of a loose term. Okay, so what we mean by margin is, if you want to stick to a textbook definition, it is defined as the distance of the closest data point from your classifier. So it is 1 by norm W. Okay, so but in our course we have kind of used this whole thing as the width of the margin. So see, margin, as I said, right, there are multiple.
So kind of basically the distance between two support vectors. I mean, both sides of the decision boundary, the closest points, the dotted lines, the distance between two dotted lines becomes the margin.
Yeah, for our course,
for
our exam, we'll keep that as the margin or the width of the margin, so to speak, right? 2 by norm W. If a numerical comes where you're asked to find the width of this or the distance between the two separating hyperplanes, it will be 2 by norm W. Okay. Yeah. So
yes, sir.
No, so now from max to min we are converting. So we are introducing this half.
No, now we are not introducing the half because of the max to min. Actually, this is 1 by norm W, right? So max of 1 by norm W is the same as min of norm W. But if you want to differentiate norm W, you'll have square roots. So you do norm W square. Okay, so norm W square is to get rid of the square roots. The half is when you differentiate, this 2 should get cancelled off. That's why you add the half. Okay,
so we inverted and took a square and multiplied it by half.
Exactly, yeah. We did all these things and all of these operations are allowed. They don't change the solution of the optimization problem. Or
Sir, will you upload this slide after the session?
Yeah, we'll upload it. Yeah.
Excuse me, sir.
Yeah.
I have a doubt. Like, will there be any case like where we don't have any support vectors on the left hyperplanes?
Good point. So that won't happen, right? So see, the idea of support vectors, the idea of SVM is to do what? Is to maximize this margin, right? So if I move, let's think about this line here. If I move this,
the moment we touch one nearest point, that becomes the support vector.
Great. Yeah. That's the correct one, right?
Yeah.
So if
There's the support hyperplane for one side, right? But the for the other side, like if there is no data like lying on the same distance from the.
Okay, I get your point. So you should. So this is the condition, right? You will have at least 2 support vectors for every SVM problem, which belong to different classes. That is a must.
Okay.
Okay. So the reason is, if you move your line closer to one of the, say, red points. Okay, so
yes, sir,
that is going to make the other side unbalanced, right? So you need to have at least 2 support vectors, one on either side of the margin. You may have more also, but a minimum of 2 is required.
Equidistance.
Kind of, yeah. So we can also slide the decision boundary, the middle line, so that it becomes the equidistance from both the margins.
Yeah. Any other questions still as far as? Yeah, so this is called, so SVM. So before we give the name SVM, right, these are called max margin classifiers because they try to maximize the margin. Okay, so any questions till this stage?
Yeah, excuse me, sir.
in the lecture, professor was discussing about the fixing, grounding the margin to 1, and then then deciding the distance to be maximum.
Right.
So how these two things are means, I'm not getting it actually.
Okay, so
When
see,
margin is 1 and then distance, maximum distance, can you please elaborate?
yeah. So very quickly, well, there are, as I said before, right, there are two different notions of a margin. Okay, so there is what is called the functional margin, and there is what is called the geometric margin. Okay, so in starting from perceptrons, in perceptrons, what did we say? We said W transpose X Y is greater than or equal to some gamma, right? We call that gamma margin. So this gamma is called the functional margin. Okay, so let me very quickly present this tab so that it becomes easier. See, you're able to see the screen now?
No, sir,
Not yet.
Okay. Is it coming up?
Yes. Scratch pad.
Okay, so yeah, so this is a functional margin. So what we call as functional margin is you have W transpose X greater than or equal to gamma, right? So W transpose X into Y. Okay, this is what we say for perceptrons or any linear classifier with gamma margin should satisfy this equation, right? For some gamma. Now, do you understand this part?
Yes, sir. Yes, sir.
Assuming you understand this part, then there is this notion that W and gamma are, I can scale them arbitrarily, right? So for example, I can rewrite the same expression as 2W transpose XY greater than or equal to 2 gamma. Okay, so what the professor has done in the slides for SVM is he has scaled this W in such a way that this W transpose XY becomes greater than or equal to 1. Okay, let's say by dividing both sides by gamma. If you want to understand it, you can understand it that way, right? So you have the flexibility of scaling W and gamma such that it becomes W transpose XY greater than or equal to 1.
Yes, sir. Mathematically, what professor has done, I got that, but I'm not able to actually visualize what is happening there. We are fixing the margin to be 1 and then claiming that the distance should be maximum.
Yeah. Good point. So see, we are fixing the functional margin to be 1. That's why I said there is this terminology of functional and geometric margin. So I'm not sure if we have time to go into that because there are like 2 more weeks remaining. So okay, what I'll do is I'm sharing the slides, right? So you can go through the slides once and maybe share this query in Discourse. Okay, I'll discuss more on that. So for now, just note this part. If you change W, your margin is going to change, right? The larger the value of W, smaller the margin. Okay, and therefore you have to choose that W that maximizes this margin subject to your constraints. Okay, in the interest of time, I'm moving on, but we'll discuss this at the end if we have time, okay? Okay, any other questions? I hope the formulation is clear, right? Because this is kind of important.
Yes, sir. Yes, sir.
It's clear till here, sir.
Okay, yeah. So now we move on. This primal dual, you need to know. This is also like important from the exam point of view. So I won't go too much into detail, but if you have a optimization problem like this, where you have to minimize f of w subject to some inequality constraints, what you do is you do some operations and convert it into this form, right? This form is important. So you minimize over w, but inside you maximize over alpha f of w plus alpha g of w, right? So this is that Lagrange multiplier, the whole thing, right? If you have done MLF week 10, you would be knowing all this. So you can now compare this with what is called the dual problem, where you swap the max and min. So that is, in the case of convex problems,
So this min max is the primal form of the initial objective function.
Exactly. Yeah. This equality always holds.
Yeah. This is like same converting with the Lagrangian min max.
Yeah.
And then from min-max to max-min is converting from primal to dual.
Primal to dual. Only thing is that if we have convex functions and certain other conditions, then strong duality holds, so they are equal, right? So the two forms are equivalent, not equal but equivalent.
Yes, sir. I had told that from min-max to max-min cannot be done generally, but only in case of nice functions like convex functions, we can do it.
Exactly, right? So that is one thing.
Sir, can it also be happen that we have max min problem as a primal and then we have to convert to min max for dual? I mean, just a query.
Okay, I am not very sure about that. So typically, optimization problems are presented as a minimization of some function subject to some inequality constraint. So even if you have a max function, max optimization problem, right, I can reformulate it as min of minus f of w, right? So I can always convert any problem into this form.
Yes, that's
okay.
Right? Okay. Okay. So in our case, in our SVM case, the primal is this min max norm w square by 2. Instead of just one inequality constraint, we have n constraints for n points. For each of these constraints, we have one alpha I, and w transpose xy greater than or equal to 1 is rewritten as 1 minus w transpose xy less than or equal to 0, right? So that's the only change. Now you just convert it into the dual, and this is what you get. So the slides are anyway shared. You can take a closer look at it later. So what we have is, we now formulate this dual. Okay, so we have a max min problem. Can someone tell me what happens from this to this stage? What is this arrow? What does this arrow signify?
Arrow means like we took a derivative and equated to 0.
Okay, that's good, right? So you have an unconstrained problem inside, right? So you have an unconstrained problem, just a minimization over w. So you can take the derivative, set it to 0, do all the algebra, and you will get w as sigma alpha a xi y. This is the most important equation in week 10 and also some part of week 11. So do not forget this. W is a linear combination of the data points, right? That's the important part.
Yeah, this is w star is summation alpha a xi yi.
Yeah, right. So that is one. And then what Sir would have done is he would have recast the whole thing into
vector form. Yes.
Right? So vectors and matrices D cross N. There is a question in graded assignment related to this, so you must know how to compute these.
Yeah, that question is only matrix multiplication kind of thing.
Correct. Yeah, that is just plain algebra, right? So nothing more than that. So you must know that given a data set, you must know to write it in this form. Okay, so each
but then
column,
that type of question takes time, sir, for calculation.
Right. Yeah, but be prepared, I'm saying, right? So just know how to do it. If there won't be too many, if at all they come, there won't be too many, right? So
okay, sir.
Yeah, so this one point some of you might miss is that y should be a diagonal matrix, right? So the label should be on the diagonal, and once you do that, you get this w, same thing as xy alpha. Okay, so you plug this xy alpha back into the dual, and this is what you get, right? So it is, you maximize over alpha greater than or equal to 0, alpha transpose 1. So did you all understand what this 1 meant in the slides?
One vector, n cross 1 vector.
Okay, right. So this is n cross 1 vector of ones, n ones, and this is, if you have done MLF, obviously you would have done by now. So this is of the form, extra alpha transpose some matrix alpha, right? So
xy alpha whole transpose xy alpha.
Right. But yeah, what I was coming to was, this is what we call this quadratic form, right? In MLF, you did 1 week of this, I think, while studying positive definite matrices and all that, right?
Mm-hmm.
So this form it should be very familiar to you by now, right? So more than this, I don't want to spend on this. Can you mute? I think there's a noise coming from your side. Yeah, thanks. Okay, so why do we go to the dual? Again, something you need to know. So there are like 3 reasons. First reason is not very important. The second one is interesting. which is that earlier you had n constraints. Okay, so you had n constraints in the primal, but now it has come down to sorry, you had how many constraints? You still have n constraints, but they are all simple constraints, right? You just have alpha I greater than or equal to 0. So they are just bounds. So constraints have been simplified. But the most important advantage of going to the dual is that the kernel appears, right? So you can replace X transpose X with the kernel matrix K of X transpose X or whatever it's called, right? So you can replace that with the kernel matrix and and make use of the whole machinery of kernels, right? So all this you must be knowing. So the most important part is support vectors, right? So once you have solved the dual problem, you will get one alpha star. This is the dual optimal point. You will get one W star from these alpha stars. This is the primal solution, right? So you have these two. Now, what is a support vector? How do you define it?
How can we solve for alpha star? I mean, how to get alpha 1 star, alpha 2 star?
Alpha star, you will solve this problem. So this is a quadratic programming problem. So there are solvers which will, if you plug in X, Y, they will give you alpha, right? So
okay. So do we need not solve in exam?
Yeah. In exam, you don't need to solve it. It's like we can't solve, right? So there are like solvers out there, packages which will give you alpha once you plug in X and Y. Okay, so yeah. So what is a support vector?
Those pointers lie on the side.
Alpha are contributing.
Okay, I got two answers. One answer was that those which lie on the supporting hyperplanes, and second answer was those which contribute to W star.
Alpha
so
is greater than 0.
Alpha greater than 0, yeah.
Okay, so it's very important because it's a very small distinction. A support vector is, by definition, this is the definition, right? A point for which alpha I star is greater than 0. This is the definition. The rest of the things follow from this definition. So what tool we use or what concept do we use to get the other parts of this package of support vectors, where they lie and all that? How do we know that? This is the definition. How do I know that it lies on the supporting hyperplane and all that?
We can construct the slackness equation, complementary slackness equation, and then putting that value and get it.
Okay, right. So that is important, right? So the complementary slackness helps us using this definition to get some results, right? So there are n constraints. For each constraint, you have one complementary slackness condition, which says that alpha I star, the dual optimal value into the constraint should be 0, right? So if a support vector, so if a point is a support vector, alpha I star is greater than 0. This means for every such point, these support vectors, right, have to lie on one of these two supporting hyperplanes. Okay, this is for sure. Okay, so this is given. Every point that is not on one of these two supporting hyperplanes has alpha I star equal to 0. Is that part clear?
Yeah, because the product has to be 0. So if it's not, the right hand side is not 0, then alpha has to be 0.
Great, right? So that is also clear from the complementary slackness condition. Now the final subtle point here is this, right? So is every point on one of these two hyperplanes, supporting hyperplanes, can we call it a support vector?
Yes.
Why?
No, sir.
If yes, why? If no, why? So
there could be a point for alpha equal to 0 also lying on the
okay, that's right. So every point on the supporting hyperplanes need not be a support vector. There could be some for which both alpha I star equal to 0 and W transpose XY equal to 1. Okay, so there could be, but to my knowledge, at least in whatever SVM, simple SVMs that we have trained, this has never been observed. Okay, so roughly speaking, you can assume that every point, every support vector, every point on the supporting hyperplane is actually a support vector. So you can kind of assume that, but I just
Could
want
you
you
please
to
elaborate a little on this?
Okay, see, if alpha I star equal to 0.
Yeah, either one of them has to be 0 or both could be 0 to make the product 0.
Correct, right? So if both are 0, what happens? The point lies
No, but
on the
then
supporting
our
hyperplane.
definition is the point
But it is not
lying
a
on the
support vector.
supporting vector plane has to contribute to the calculation of W star.
No, right? No. The definition of a support vector is only those points for which this is greater than 0. Only those points contribute to W star, right? This is a summation over all these data points. If alpha I star is 0, then they don't contribute, right?
Even though the product W transpose XY is equal to 1.
Yeah, even if W transpose XY equal to 1, what contributes to my W star is those for which alpha is greater than 0.
Actually, sir, alpha star equal to 0 means your optimal W is 0. But in the very beginning, from the classifier, when we are finding the line, because this line is always passing through the origin, we are taking all W except that 0, 0. So here, this thing means violated.
So if
alpha is equal
if
to
it is
0.
both are 0, then it is little confusing.
No. See, I'm not saying every alpha I star is 0. I'm saying that there could be a situation where, for some point, both alpha I star equal to 0, and that point lies on the supporting hyperplane.
Okay, understood. So it could be
Okay,
0.
but for the exam point of view and in general, assume that it's okay to assume that all points that lie on the supporting hyperplane are support vectors. Okay, so
Means for them alpha has to be more than 0.
Yeah, for them alpha has to be greater than 0.
Okay.
Okay, is this point clear to everyone?
Yes.
Okay, so yeah, so this is like a quick summary of what hard margin linear SVMs are. So by the way, for the exam, we are using this following terminology. We are using hard margin linear SVM to mean one without any kernel. Okay, so you should not get confused when you see this term linear SVM. It's not something new that we have not done in the course. It just means it's the vanilla SVM without using any kernels.
So kind of
hard margin,
the decision boundary is straight line.
Yeah, decision boundary straight line, and hence the term linear. Okay. Okay, so to summarize, what happens in SVMs is you give one data set as input to some SVM solver that is going to solve the dual problem and return n values, this alpha star. You can use that to construct W star, and once you construct W star, you can draw the separating hyperplane. Those for which this W star transpose X Y equal to 1, they will all lie on these two supporting hyperplanes, and those for which alpha is greater than 0, we call them support vectors. Okay, so this is the overview of what is happening in SVM. The final point about hard margin linear SVM is this is how prediction is done. Prediction is done like in any linear classifier, whether it's logistic regression, perceptron, SVM, or some arbitrary linear classifier. The prediction doesn't change. So some of you might have this question: if a point lies between the margin and the decision boundary, should I classify it as 1, or what should I do? The answer is, if it is on this side, then it's 1. If it is on this side, it's -1. So in the case of prediction, margin doesn't matter. Okay, is that point clear? All linear classifiers we predict in the same way.
Yes.
Okay, right. So that is hard margin linear SVM. So from this we jump to soft margin. I'll just briefly touch upon this. Whatever is relevant to week 10, then Nitin will continue. So if your data set is not linearly separable, there are two possible ways this could happen. One is a structural nonlinearity, and so yeah. So can you mute someone's mic? Yeah. So the structural nonlinearity is when you can satisfy that, or you can solve that using kernels, right? So we have been seeing kernels from week 1, week 2, right? So you can use what is called this hard margin kernel SVM. Using the kernel trick, you can solve that. But there are statistical kind of nonlinearities, right, which are because of outliers. So for example, you have a data set like this. This is not linearly separable in the second sense, right? You can't find a line which will separate them no matter how hard you try. So there is no point of using any kernel, right? So whatever kernel you use, the problem is not going to solve, because this is the decision boundary is linear, but it so happens that we have two outliers, one green here and one red here, right? So in these cases, what you do is you use a you add this extra term called psi I or epsilon I. So professor calls it bribe. So you use this non-negative bribe to push these points to the right side. So how much bribe should I pay so that these points move to the right side of the decision boundary, and that gives you the soft margin formulation.
So if we
Okay,
want
so
to
for these
visualize
points,
it, after, how the points will look after paying this bribe visually?
after paying this bribe, so for example, if you look at this green point here, so this is the green side, okay? The right hand side is the green side. This is one outlier. So this outlier has to pay some, actually this I have drawn it incorrectly. This line should be from here to here. So it has to pay a bribe of this whole distance. I will correct this, but this much by bribe it has to pay so that it can go and touch the correct supporting hyperplane.
Okay.
Did you get that part? So 1 minus C, this is W transpose X
For
equal
that
to 1,
particular
right?
ith point, that much has to be added.
Yeah, for this data point, this whole distance from the ith data point to this correct supporting hyperplane, you have to add that much as the bribe. Only then it can go to the correct hyperplane, supporting hyperplane.
Okay.
Okay, so that is all for week 10. I'll just add few more things from the exam standpoint. So you must know this terminology for SVMs. There is hard margin linear, hard margin kernel, and soft margin linear and soft margin kernel. Okay, so you need to know when to use what. Okay, and yeah, the rest are all like things that you already know. Okay, any questions? If not, we'll move on to week 11.
One doubt over here. In activity question 11.3, question 1, right? So there is a condition like if the W star T transpose Xi Yi less than 1, so what should be the right statement? So in that, it is mentioned like ith data point lies between the supporting hyperplane. How can we, it is sure that it is only in between the supporting hyperplanes? It can be below towards the negative side as well.
W
If it is less
transpose.
than 1.
Nitin,
W
you want to
transpose
clarify?
Yeah, okay. So we'll talk about that. All those conditions we will talk briefly in the next session. I mean, the next part of this session. So there may be answer may be given wrong. I will check that out. So you mentioned that W transpose Xi by I is less than 1, right?
Yes.
Then
So how
it means
can
that
we show that?
W is actually incorrectly classifying that point, or if correctly classifying, then that point must lie in that within the margin. So that we will all talk about in this next part.
Right.
Okay, any week 10 just related to week 10, let me know. If not, we'll move to week 11.
Yes, sir. I have one doubt. Are we only working with like centered data set in SVM because our weight vector that always passes through origin?
Okay,
That
actually,
separator.
yeah, that doesn't have to do with centering. So a data set may be centered and still your optimal decision boundary need not pass through the origin, right? So it doesn't have to do with centering like in the case of PCA, but your observation is right. For the sake of convenience, we have dropped this bias term in our discussion. So typically, you should have one W transpose X plus B equal to 0 as the decision boundary. But for our course, we stick to.
So like if we want to add that bias as well, so we have to like add dummy feature to matrix and carry the things like linear regression, right?
Yeah. Like I think Sir would have mentioned this in week 12. You have to add one, dummy and then.
Okay.
So
So
in
question
SVM,
1 of graded assignment week 10.
Once again, so I think Shivansh, Shruti
Uh,
have raised their hands. Harshit, you can also raise your hand. I'll finish with Shivansh and then come back. Yeah.
yes, sir. I just had one simple question. How important is kernel SVM in context of the examination?
The context of examination, it is important because kernels are like uh, only way to, so see, from the context of the course, kernels are important because that's the only way we address nonlinear data, right? And all real world data is going to be undoubtedly nonlinear, right? So some kind of kernel we have to use. So from the exam you must know what kernels are, right? So starting from
Yes.
week 2 in then kernel regression, kernel SVMs, if you know what kernels are, that should be enough.
Okay. So, sir, the information that we learn in week 2, 3, 4 regarding kernels, like we learned in conversions and all those things, all that will be enough, or do we need to understand how we would use a kernel with the SVM as well?
No, that is enough because once you know how those, once you must know for the purpose of kernel SVM, you need to know how to compute the kernel matrix. That is all, right? This X
Okay, sir.
transpose X.
Yes, sir.
Yeah,
That
yeah,
is all right, sir. Thank you, sir.
yeah. Yeah, Shruti, yes, yeah.
Sir, I have doubt in activity question 10.5, question number 4.
Okay,
Like
what is it about?
it's about like complementary slackness conditions. So I'm not able to prove two options, first and second option.
Okay, we have, okay, just 2 more minutes. I'll just quickly
I
see.
share my screen. It's open on my.
No, it's okay. 10 week 10,
Yeah,
10.4,
5.
10.4.
10.5, sir.
Okay, 10.5, question 4 is it?
Uh-huh. So the first one is Lagrange of W alpha star. So like answer to that is f of W plus alpha star G of W, right? And because we are applying complementary slackness, so alpha star G of W would be 0. That's why the answer is f of W, is it?
1 second. I'll just share this. F of, you're saying option A, is it f of W star equal to,
Yeah.
you're asking why is that correct?
Yeah.
So, see, this is actually, this is not just the complementary slackness. I think these are the, okay, wait 1 second, I'll read the question. Using complementary slackness, okay. Okay, so this last option is what is called the stationarity, right? So this comes from KKT conditions, if you remember.
Okay.
Okay.
I thought we are finding the value of W star at the gradient, and it's kind of optimum, so it would be 0. That's how I thought.
Okay, the
I
first one,
have doubt in option A and B.
option A and B. Okay, see at the alpha star is the dual optimum, right?
Yes.
So f of W star is equal to, so f of W star is what? The optimal solution of the primal. So I mean the optimal value of the objective function of the primal, right? So this
Okay.
and dual are equal. Correct. So by strong duality, the optimal value of the primal and dual are same.
Okay.
Okay. So this is what, this is max. So this is actually what, max alpha greater than or equal to 0, minimum of this, right? That's the dual problem. And this, you have already fixed the alpha star. So you don't need the max anymore. So what remains is min W L of W comma alpha star. So the minimum value of that part has to be equal to f of W star.
Yeah.
Okay, is that satisfactory or?
Because alpha star GW would be 0 by complementary slackness, isn't it that?
Alpha star W G of W star would be equal to 0. That is true. But this is
That's
the
why the answer is f of W. That's what.
okay, you can put it that way also.
Okay.
So L is f of w plus alpha g of w. So you're saying at alpha star g of w star, that thing vanishes. So this is f of w star. Yeah, that's also fair enough. Yeah.
Okay. And in second one?
It's whatever you have said, right? Because of complementary
Okay.
slackness, alpha star g of w star will vanish.
Okay.
And f of star w star will only remain.
Okay. Thank you, sir.
Yeah. Any other questions? If not, we'll move to week 11.
Graded week 10, question 1.
Graded week 10. Okay.
If you can elaborate on the solution.
So what is the question? You have three. These are all what? These are all linear classifiers, is it? W1, W2, W3. Yeah, okay. All these are linear classifiers which satisfy this inequality, right? So you're asking how do the norm values or the lengths of these,
All the three weights are having different norms.
they are having different norms, yeah. So for the SVM, we are trying to minimize norm W square by 2, right? So that will have the smallest norm. The SVM's weight vector will be having the smallest norm, right? Because
No, it is saying hard margin. W1 is hard margin SVM, hard SVM.
yeah. So what are you trying to optimize? You are trying to minimize norm W square by 2, right? For SVMs.
Correct.
So see, what can you say about W1, W2, and W3 for this optimization problem? What kind of points are they? If W1, W2, and W3 satisfy these n inequalities, what can you say about them? As far as this solution, as far as this optimization problem is concerned, what are W1, W2, and W3 called? There's a name for them.
I mean, they are weight vectors, no?
They are weight vectors, but if you look at it from the point of view of an optimization problem, W1, W2, and W3 satisfy these constraints. So what are they? I hear the answer somewhere.
Sequence?
No. You have to think about it, right? So just think about it a bit, but if you still don't get the answer, let me know, we'll discuss it. Okay, but just the hint is you are trying to minimize norm W square by 2. So the SVM will naturally have the smallest norm, right? The classifier returned by SVM should have the smallest norm among these three. Is that clear or still not clear?
No, it is saying W1 is hard SVM weight vector. And suppose W2 and W3 are also from SVM.
That
Can
can't be
it be
right.
so?
No, that can't be right. So if that can't be because of this line, right? This line that they have different norms. So you can assume that all three weights are different norms. So the SVM is it's a convex optimization problem, right? So you can't have different. It can have only one minimum objective function value. Okay, so just think about it anyway. So I think that is all we have for week 10. Shall we move on? Week 11?
Sure.
Yeah, thank you, guys. So, am I audible properly?
Yes.
Okay, well, let me share my screen first. Okay. Is my screen visible?
Not yet. Now it is. Visible now.
Okay. Okay, can you see the slides?
It's week 11 revision.
Yeah, okay, sure. So in week 11, we will start the stock margin and then we'll move to the next part, which is ensemble methods. Okay, so Karthik has already explained by where the hard margin SVM formulation fails and how we tackle this problem, right? So just to sake of continuation, I just explain it quickly. So remember, hard margin have this formulation where we try to minimize norm of W square with the following constraint, right? So this constraint says that actually the W that we are looking for actually correctly classify xi with some margin, right? So this constraint says that point xi is away from the supporting hyperplane, correct supporting hyperplane. Means that the positive points are away from the or on the right side supporting hyperplane, and the negative points are on the left side of the left supporting hyperplane, right? So that is the formulation for hard margins SVM, but this formulation fails when there an outlier comes into the picture, right? The structure is, we assume that structure is still linear, but the definition of linear separability is lost just because of some noise present in the data set. And there we cannot find such W where this constant is satisfied, right? Because just because of those noise. So tackle this problem, we add some bribe to the data points such that data points come to the with that bribe, that data points come to the right side, right? So that leads to us to the short margin formulations where we add some bribe to the data points, positive bribes to data points to make sure that that noise or that outliers comes to the right side of the right side in the data set, right? And so this becomes our objective function now. So if you look at this objective function, so w equal to 0 is the solution of this problem with all xi is equal to 1, right? So it means that, so if you set all xi is equal to 1, then this constraint is satisfied. Again, with w equal to 0, this constraint will be satisfied because this xi will be 1, and this w0 will be the minimum value for that w. So this objective function has the solution w equal to 0 with all points are paying some bribe, and some actually one bribe equal to 1. So tackle this issue. What we do, we rather than minimizing norm of W square, we minimize some of bribes as well, right? So it makes sure that all points need not to pay bribes. And here C is a hyperparameter which actually which actually depends upon the distribution of the data set and all, and it is set it is this value of this is calculated using some cross validation functions, cross validation techniques and all. Okay, so this becomes our short margin formulations. Okay, so any doubts till this point?
Sir, C is hyperparameter. What is it called?
What this is called? Does it have some name? If it has, I don't remember any particular name for
Sir
that.
didn't use any name for it. It's just introduced as a hyperparameter.
Yeah, as a
Okay.
hyperparameter. Even I don't remember any name if it has any particular
Sir,
name.
sir said it has a cost of bribes.
Yeah,
I think
the
it's kind
purpose
of
of C,
penalty.
purpose of C is to like how much, what is the cost of each bribe.
It just may depending on its values actually depends upon how the data set is distributed. If there is large margin within the positive and negative class, then C may be larger, or if there is very less margin within the classes, then C may be very small. So depending upon the distribution, C may take different values. So it's actually set using some cross validation techniques. Okay.
Okay, sir. Thank you, sir.
Yeah. So any other questions till this point? So we till now we have the formulation for source margin problem. Now we have to solve this optimization problem. Then we are done, right? So the solutions of this goes in the same manner that we have done for the hard margin. We convert into the primal and dual formulation. So the Lagrangian function for the same will be, remember we will convert the constraint into the less than equal to 0, g of w less than 0 form, and then we will form into the Lagrangian function. So the Lagrangian will be of this kind. Okay, so here it will be minus xi I as well, and this will be by I, and minus beta is xi. So this will be the Lagrangian for the this objective functions, and then primal becomes minimum over w and psi, and over the maximum over alpha and beta of the Lagrangian function. So this will be our primal formulations of the same problem. So the primal variable gonna be w and xi, and if you look at this constraint and all the objective functions, they all are convex functions. So we can strong duality holds in this case, and we can convert the min max problem to the max min problem, right? Just because of those constraint and all the objective function are convex. Right. So the dual problem will become max over alpha beta min over w xi of the Lagrangian function. Okay, so I missed out xi i's here, so you make sure that xi i's are present in this Lagrangian function. Okay. Now, so same thing. We will take the derivative of this Lagrangian function with respect to w and xi. Remember, now we have two variables w and xi. So we'll take the derivative with respect to w and xi to solve this minimization problem. So if we set of the Lagrangian derivative of Lagrangian with respect to w to 0, we will get the w star as the same thing, summation over alpha I xi by I. So again, w star is the linear combination of the data points, right? For all the data points. But the good part is that all those data points doesn't come into pictures to define w star. For most of the data points, this alpha I is actually 0. So only this w star actually the combination of the some points of the data set, not all the data points. Okay. And again, if we set the derivative of the Lagrangian with respect to xi I equal to 0, then we will get the equation alpha I plus beta equal to c. So this is the difference between hard margin and soft margin, where their alpha was not upper bounded. But in the case of soft margin, if you look at these, both alpha and beta I is positive and c is again positive. So this alpha I is upper bounded by c, right? And obviously these are positive quantities. So alpha here in this case, alpha upper bounded by the value c. So alpha can take value between 0 and c. So if you again set this value, put this value back into the Lagrangian or the duality problem, we'll get this dual problem as the same that we have done. But here alpha actually is upper bounded by c. So this is the only difference between soft margin and hard margin in the context of formulation objective functions. Here alpha is actually are upper bounded by alpha. That is why it is called box constraint, because they have only lower bounded by 0, right? But here in the case of soft margin, they are upper bounded by c. So these constraints are called box constraint. And again, this dual problem has the terms x transpose x. So this again can be canalizable, right? So this is the solutions of soft margin formulation. So any problem at this point? Okay, if not, we can okay, so we can move to the different cases. And before that is the complementary selection condition, again the same. This the constraint times that variables must be 0. So alpha star times this constraint equal to 0, and the second constraint is xi I. So beta I times xi I should be 0. So these are two complementary selection conditions in the case of soft margin SVM problem. Okay, so what happen if b sets equal to 0, right? So if b sets equal to 0 becomes to the same problem, right? Here this one, where we said that the problem of the solution of this objective function is 0, right? And so if you look at in the other way, if b sets equal to 0, alpha becomes 0, because alpha is upper bounded by 0 and the lower bounded by 0. So alpha has to be 0 in this case. So if alpha is 0, it means that the w star will become 0, right? So, and that is what we have already looked, right? So if c becomes 0, then actually the solution of that problem becomes 0. And if the c tends to infinity, then there is no upper bound on alpha, and the formulations are the same as hard margin formulation. So these are the case, then c becomes 0 and c. Okay, so this is infinity, c tends to infinity. Okay. Now let's look at some cases depending upon the positions of different points corresponding to the hyperplane and decision boundaries. So the first case where w transpose xi by I greater than 1. So it means that w star is actually correctly classifying the ith point. It means that the positive points are on the right side of the hyperplane and the negative points are on the left side of the left supporting hyperplanes, right? So in this case, if you look at the very first this terms 1 minus w transpose xi by I minus xi. So look at this w transpose xi by I greater than 1, strictly greater than 1. So 1 minus this is strictly negative quantity, right? So it's negative minus something positive. So it's this term is strictly negative, right? So if this term is strictly negative, then from the first complementary selectness condition, we can say that alpha I has to be 0, because this cannot be 0, it is strictly negative. So alpha star has to be 0. So any point which are correctly classified by that W star, they, for those points alpha I is equal to 0. It means that they are not playing any role in defining W star. And if alpha star is equal to 0, then what is the value of beta I? It has to be C, because the summation
C.
is always C. So from the second complementary slackness condition, you can say that the xi I has to be 0, right? It means that that point is not paying drive. So any point which is correctly classified by W star, or just think those point as away from that hyperplane, supporting hyperplane, right? Positive from positive points away from the right planes and negative points away from the left supporting plane. For those points, they are not paying any drive and they don't play any role in defining W star. Okay.
Yes, so kind of saying that those points are correctly classified and they are no outliers.
Yes, they are not outliers. Next case is where the points for which this condition holds. Okay, so this condition says that the ith point is on the correct supporting hyperplane. Correct means the positive are on the right supporting hyperplane and the negatives are on the negative supporting the left side supporting hyperplane. For those points, if you look at this first complementary selectness condition, 1 minus W transpose xi by I will become 0. So we will left with this equations, and this is the second complementary selectness conditions. So if you solve this condition given that this alpha and beta should sum to C, if you solve these equations, you will get xi I equal to 0, and it's easy to see as well, because both has to be 0 only when that alpha becomes xi I has to be 0, right? So it means that any points which are lying on the correct supporting hyperplane, they are not paying any bribe. Okay. Okay, so can we say anything about beta here? Beta is 0 or non-zero? We cannot say, right? It can be 0, it cannot be 0 by the second complementary conditions, because xi is 0, so that is making it 0, but beta can be 0 and greater than 0 as well. So we cannot comment on that, and so for we cannot comment anything on alpha star as well. And that we have already seen that any points on lying on the correct hyperplane, it alpha values for that may be 0 or may not be 0. Okay.
So beta can be between 0 to C, right?
Yes, beta also is upper bounded, so it is also 0 to C.
So that is how we are saying that all the points on the supporting hyperplane may not be contributing.
May not contribute, may contribute or may not contribute for defining W star. But what we can say for certainty is that they are not paying any bribe, because they are on the correct hyperplane, correct side of the hyperplane. Okay, is that clear? Okay, so let's move to the next part. The condition for the xi says that W transpose xi by equal to less than 1. So it means that W star is either incorrectly classifying that xi point, or if it is correctly classifying, then that xi point is lying between that supporting hyperplane. So this equation means that. Okay, so for that, so this is your first constraint, right? Where that W transpose xi by I plus xi has to be greater than 1. So this is your first constraint. So if you look at this quantity, from here you can conclude that this is strict. This 1 minus this has to be
Sir, how
strictly
it can
positive.
lie between the margins? Because we are assuming that there is no data point between the margins.
No, for outliers, they may be outliers.
No, they are outliers, but then between the margins, can any data point lie?
Yeah, so soft margin can take uh, uh, such conditions as well, where that there may be some points within the margin as well, and they pay some bribe
No,
and go
ultimately
to
it
other
remains
part of that.
an SVM problem. So even outliers are there, they might be on the wrong side, but can it be so that
Yeah.
the point is
So
between the
as soft
margins?
margin takes care of both things. One thing is that if there is some outliers that is on the wrong side of that distribution of classes, but there are some points which are actually the data set are have large margins. Just because of some points, these margins become very less. So SVM soft margin SVM takes care of that conditions as well. That makes sure that the supporting planes becomes away from that, and we that those points again pay some bribe. Okay.
So graphically, I mean pictorially saying, we are drawing two margins, I mean dotted lines, and data point can lie between those two dotted
Yes,
lines.
yes, it can lie between those.
Okay.
So, which is mentioned in the activity question, that is, it should be between the hyperplanes only. So that statement must be wrong, right?
That must
It
be
can
wrong.
be incorrectly classified and beyond the another side of hyperplane, right?
Yes, 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 absolutely.
Okay.
Okay. Okay, so from these conditions, so this becomes strictly positive. So it means that that point is actually paying some bribe, some non-zero bribe, right? So if xi is strictly greater than 0, then from the second conditions, beta I has to be 0, and it means that alpha I for that particular point has to be c, right? So it plays some role in defining W star, right? So these things you should know. If you are not
So if
comfortable with this,
C is a hyperparameter which we tune manually,
yes.
so alpha I is equal to C. What does that signify? Yes, it is non-zero and it is contributing to W star. Anything more than that?
And so from there you can values of C actually depends upon distribution. So if there is large margin, then they may pay their role on defining the W star may be higher. Something like that you can think of.
Okay.
Okay. Okay. So any other doubts till this point? If not, we can move to the other part.
Hello.
Yes.
Sir, I think there was a question in the, what do you call it? NSEM practice paper, the last one.
Okay.
The NSEM practice paper.
Okay. What is
It
the
had
question?
it had four images with four different soft margin linear SVM models with different values of C, and we had to kind of guess what the values of C were, or like how they compared against each other. You
Yes,
said
yes,
if the margins are big, then C must be higher.
Yes, yes, something like that.
Yeah, but in the answer for that question, it was actually the opposite.
Okay.
C1 had the highest margin, but the value of C1 was the lowest.
Okay, so I have to check that. So I may be wrong at this point that for the larger margin, C has to be larger. So I will confirm that. Okay.
Okay, thank you.
In the case of this double star transpose xi yi equals to 1, so is it necessary to have the bribe equals to 0?
For which for what you are talking about?
In the condition of equals to 1.
Yes. Then yeah, for that xi has to be 0. That is, they are not paying any bribe.
But according, if we can map that in this situation, alpha can lie greater than equal to 0 and less than equal to C.
Yes.
Right?
Yes.
So if alpha can be less than equal to C, in such a case, if alpha is equal to C, how can we say that bribe is 0?
Okay, so that
Because
we are coming
if
to that
alpha
part.
is equal to
Yeah.
C,
So I
then
got your
beta
point
must be
where.
0.
Yeah, so we are coming to that part where you mentioned that if alpha takes value between 0 to C, then xi has to be 0, right?
Yeah. So how
Yeah,
it
so
can be?
we
Because we
will
can't comment on the side. Because beta will be 0, then we cannot comment on the bribe that it will be 0 or not.
no, but what I'm saying that if xi is equal to 0, then we cannot comment on the value of alpha.
No, xi is multiplied with the beta, right?
Yeah.
So when a situation is that alpha is equals to C, so if alpha is equals to C, in such a case, beta will be 0,
Yes.
right? And if beta is 0, then how can we comment that psi will be 0 or not?
It if beta is equal to 0, then xi need not to be 0. It can be 0, it cannot be 0.
Exactly.
But it can be 0 as
So
well, right? It can be 0 as well.
it can be 0. It can be 0, but not mandatory, no?
Not mandatory, yes.
right? But in the activity question, it is mentioned that it is a mandatory that it will be equals to 0 only.
Where? Which question?
Activity question 11.3, question number 2.
Okay, I'll look for that question. 11.3, question number 2. I'll look for that question and we'll come to that.
Okay, thank you.
But my point is that if xi is equal to 0, then we cannot comment of the value of beta and alpha. Just because it can be 0 and it can be strictly greater than 0 as well, right? Okay, so let's look at the other part where we'll look at the values of alpha and we'll try to find out the possible values, possible positions for that point, corresponding points. Okay, so let's assume that alpha is equal to 0 for some point, ith point. So it means that it plays no role. It plays no role in defining W star. So from there you can say that beta I has to be C, right? So you just take all as star, beta I star, xi I star. So all beta I has to be C. It means that xi I has to be 0. That is any point that is not playing any role in defining W star is actually paying no bribes, right? And from the first complementary first constant, you can say that if just set xi equal to 0 and the first constant becomes this thing, it means that W star actually is correctly classifying that ith point. It's very clear as well. If and for any point if alpha is 0, then they are correctly classified that W star. Okay, so it's an easy part here. If you move to the second part, where alpha star equal to C, in this case beta I becomes 0, and this has to be here from the first complementary slackness conditions, because alpha is equal to C, so this has to be 0, right? So and beta is equal to 0. So from here if you look at xi I is equal to 1 minus W transpose xi by I, and xi I is actually is always positive quantity, strictly positive, second constant. So from if you put the value of xi here, from here 1 minus this thing, it means that 1 minus this has to be greater than 0. It means that W transpose xi by I is less than or equal to 1. Okay, so it means that if the value of n for any data point, if value of alpha is equal to C, then that point is actually incorrectly classified, or if it's correctly classified, then that must lie within the margin. Okay. So let's move to the third part where alpha is strictly between 0 and C. So if has then beta has to be between 0 to C, because sum is always C. So if it is strictly between 0 to C, beta I again has to be between 0 to C. So from the second condition, xi I has to be 0 and xi I has to be 0 from the first conditions, because again alpha is not 0. So so this 1 minus W transpose xi by I minus xi I, and xi I is equal to 0. So this has to be 1. It means that if for any point if alpha lie between 0 to C, it's, then that point lies on the correct side hyperplane, supporting hyperplane, right? Don't be confused within whether alpha equal to C, then this happening, and if this is happening, then this is true. So if you are confused within these things, I recommend you just to go through those slides and write down by yourself all these things and look what's happening when there. If you know the position of the point, then what can be
Yes, sir.
possibly
Those three conditions, basis three
Yeah.
conditions, we can derive this.
Yes. Based on the complementary conditions and the
Yes, sir.
constant, you can derive all these things. No need to by heart all these things. Just the intuitions and the ideas. You should have ideas what's happening out there, right? Okay. So this is all about short margins SVM. We can move to the next part, which is ensemble methods. Okay. So before moving to the ensemble method, there two terminologies we often use in machine learning, which is overfitting and underfitting. And you all must know, I think, for these two things, overfitting and underfitting. So what is overfitting? So if we try to fit the noise, or say if we try to fit each and every possible data points, then that model is called overfitting. In this, what happens that the model becomes more complex, or say the decision boundary becomes very complicated.
We are trying to find
So in this
a
case,
function in the D dimension, and sir had told that in D dimension there will definitely be a function which will model all the input data points. So that
Yes,
kind
yes.
will be overfitting.
Yeah. So we are trying to fit every point, or say we are trying to fit noise as well. Then in that case, what will happen? Training error will become very less, right?
It will be
But
zero for a particular
yeah,
function.
if it is fitting every single point, then training error will become zero, right? And what happens to the test error in that case?
Very huge.
It may go high, right? Because just because we just try to model only those points, or we try to fit only those points which are in the training data set. So test data point can be different from those points, and test error may go high. So in the case of overfitting, training error is very less and the test error is very high, right? And what is underfitting model? So in the underfitting model, we actually missing out on the real structure of the data set. Let's say your data set is had quadratic distributed, but you try to fit the linear model over there. So you are actually missing out the real structure of the data set. So in that case, training error will be high, right? So in that case, training error will be high. And what about the test error? Test error is again high
That is
because the
definitely
test
going to be
data set
high.
and the
Yeah.
training data set comes from the same distribution. So actually, you are missing out on the structure. It means that the test error is again will be high. So in the case of overfitting, on the case of overfitting, training error is low and test error is high. But in the case of overfitting, training
Both
and
are
test
high.
both are high, right? Okay. So this is what we mean by overfitting and underfitting. Okay, so our fitting models have high variance. High variance means that if you make subtle change in the data set, or say you have some model f of w for that, and you just start you again model it using same data set, but you make some different hyperparameters and use some different initializations. Then in this case, that model may be differ from the previous one. So it means that those models on the same data set, or some making some subtle changes in the data set, those models are are differing from each other uh, on the grade node. So in that case, there will be high variance in the case of overfitting models, but in the case of underfitting models,
High variance it will be because of there will be so many wrong predictions, and that variance will be high in that because of that.
yeah, because just making some changes in the data set, or just changing the initializations, your models may become very different, right? Because remember, in the overfitting, we try to fit try to
Yes, so in
fit every point.
overfitting,
So
the test data prediction will be I mean, kind of totally different, and that is why variance will be very high
yeah, you
on
can say
test
that.
data.
Yes.
On test data,
Yeah,
because
you
on
can say.
training data there won't be any variance.
Sorry.
On training data, it will not be high variance. It will be on test data.
No, variance in the sense of we talk about that models. The models have high variance. It means if we make some changes in the data set, or just make some different values for hyperparameter, those models can be very different to each other on the same data set, right? So remember, if we have some data set, and we are fitting each and every point, and we make some changes, or say we take some different data set with the same distribution, then those models may be very different to each other in the structure, right? So in that sense, we call those have the high variance. They are differing to each other. Okay. So overfitting models actually suffers from the high variance, and underfitting models actually suffers from the high bias. It means that they don't make predictions well on the even on the training data sets.
So,
So
what do
is it
we
mandatory
mean?
the
What is high
underfitting
bias on
models?
underfitting?
I just lost what you said.
High bias on underfitting. What do we mean by that?
Mean by that is that even if we make some changes on that, and we are not worrying about the real structure of the data set, the example that I just took, where the data set is quadratically related, and we are only fitting the linear model for that. Then if you make some changes over the data set, your that model will be it means that will be centered out some, the model will not be differ by much. It means that their value will be the model will be centered out some point, not say some linear line in the case of linear model, and depending on that what models you are fitting for that data set, there won't be much difference over those data point, those models.
So my query over here is, in the underfitting model, we have the high bias. So is it mandatory that it will have a low variance?
Actually, there is always a trade-off between bias and variance, but it's always not true that high bias will always will have low variance.
Exactly. But in the question, we have an option like for the underfitting model, what we may have the high bias, high variance, high bias, low variance. These kind of options are available.
In
So
general,
the
in
true
generality,
one is,
you can say that they have high bias but low variance.
but how can we comment on the low variance until we test on the test data? Right. For the overfitting, we can say that okay, it is the bias is very low because it is overfit, and then variance will be high because of that overfitting. But in underfit, if it is not getting the proper results on the train data only, then how can we comment that it will get the better result on the test data?
No. High variance, low variance doesn't mean that it performs better on the test data set. It means that those models won't differ if you make some changes in the initializations or some changes in the subtle changes in the data set. Then model won't be differ by much. That is what meant by the low variance.
But in general, what we say is the training error is considered as a bias, and the testing error is considered as a variance.
No. It
Isn't it?
doesn't mean that test error is high, then it has high variance. It doesn't mean that.
No, if what we call for the variance, that is the testing error, isn't it?
No. Testing error is not variance. Variance is actually we talk about the model. So how the model are differing if we training different models, same models. I mean the different model in the same data set, then their structure may be very different. Then we call those have high variance.
Now, how can we calculate that variance on the training error, training set? For trainings, for calculating the variance, we need to have the testing set.
No, it doesn't like that.
So can we say that for the underfit model,
Hmm?
since the model is underfit because of the main structure get missed by the
Yeah,
data point.
yes. Because
So
we already
uh,
missed out on the real structure of the data set.
yeah, so the data sensitivity in the model that we are fitting under the underfit model is
Hmm.
very low. So wherever the sensitivity of the data with respect to model is low, generally it has been seen that the variance of the output is once again low.
If the bias is high, you mean, right?
Bias is high.
Okay.
Since the structure is missed,
Hmm.
the data is not that sensitive to the model that we are feed, that
Yes,
the
actually, yes,
underfit.
exactly. So in that case, if we miss out on the relay structure, then bias will become high and the variance will become low. Okay, so you will study deeply around this bias and variance in the next future courses. But for now, just think overfitting as the model which have low training error and high testing error, and the underfitting models are ones which have both training and test error high. Okay,
Actually,
they
I
have a
got this concept from the ML future course of MLP only.
not
In that
MLT.
course,
Maybe you will study in deep learning courses about more deeply in this
yeah,
concept
but
about.
in MLP it is mentioned like that high bias is related to training data and the high variance is the error on the testing data. So that's why I mentioned this point over here.
You can connect those points, but it's not that high variance with high training error means that high variance. It doesn't mean that. You can connect those points.
Okay, thank you.
Okay. Okay. So the point is that overfitting models actually suffers from high variance, and the underfitting model suffers from high bias, right? And error is actually combination of both bias and variance. So we don't want model to be overfit and underfit as well. Okay. So to overcome those problems, we have some techniques which are called ensemble methods, and those are only for those which have high variance and high bias or high bias. Okay, so ensemble actually means that we combine the results or we combine the outputs from the different estimators. Estimator means the classifier, or in the case of regression, regressor, right? So there are two mainly ensemble method. One is called bagging, and another is called boosting. So we will covering random forest in bagging and AdaBoost in boosting. Okay, so let's start with bagging. So bagging stands for bootstrap aggregation. Okay, so what we do, we here in bagging, we train m different, let's say m different estimators on the on m different training data set. So we have on given original data set x1 to xn. So to train m different estimators, we need m different training data set, right? So to create m different training data set or call bag, we generally call them bags if we creating using the bootstrap sampling. So for creating them, what we do, we sample from the original data set, but with replacement. So assume that you have this data set x1 to xn, 10 data points are there in the original data set. Now you have to create one bootstrap training data set from there. So what you will do, you will collect the samples from this original data set, but this replacement. So it makes sure that this bag that you have created is different from the original data set, right? So just because there may be some multiple data points here. So if you look at here, X8 is
So
repeating.
frequency of one data point could be more than one in
Yeah, so
bootstrap.
it may end up being multiple times in that bag, right? So it makes sure that these training data set are different to each other. So in that manner, we create m different bags. Okay, and we train m different estimators over those training m different bags. And for making predictions, let's say we are making predictions for some point x1, we take the outputs from all those m estimators and we'll check the majority class. In the case of classification, so the majority class will win, and that will be the final prediction for that. So that is all bagging. But so only point here is that we create bootstrap samples, bootstrap bags, and then we'll train m different estimators and then take the aggregations of those outputs, right, to make the final predictions. Okay, so in a bag, on an average, 67% data set is coming from the original data set, and around 33% of the original data set doesn't end up being inside in a particular bag. Okay, so this you can check. It's not hard to think. Okay, so one more point about bagging is that we start with high variance. Bagging reduces variance. So in the bagging, the estimator that we use tends to overfit. Okay, it's not like we can use any
Yeah,
model,
excuse me,
any
sir.
estimator there. Yes.
Excuse me, sir. Sir, as you mentioned that 67% of the data will be used from the means original data set, and 33% will not appear. It
On
means
an
that the
average,
remaining 30, on an average, it means that 33% will be repeated.
3% will be
repeated. I mean, in the data
no,
set,
it means that
33%
let's say this is your first bag. Okay, so in this around 7 data points are same as which are in the original data set, but
This is
three data
because
points
of
are
repetition.
repetitions here.
yeah, these three are repeated.
These three are not selected in that bag.
Not selected. Okay.
Not selected
So
in that bag. So
only 67% data will mock as 100%. I mean, there will be some repetition, but we cannot say how much will be the repetition.
yes. It's on an average that on an average 33% of the original data set will not be inside that in a particular bag. Okay, it's just probability questions, right? You just need to check whether the point will
No,
inside the bag
this
or not.
figure you told basis some empirical understanding.
Yes, exactly.
Okay.
Okay. Okay. So the only point that I want to make here that in the bagging we uses the high variance models, that the model which tends to overfit, we use bagging. So generally in bagging, the decision trees are preferred. The decision tree with the maximum possible length, they are preferred for the bagging. You can use any different model, but you have to make sure that those models are actually having high variances. Because if you taking models, if you're training models which are having low variances, then bagging will be insignificant because bagging actually reduces variance, because you just think bagging as final prediction is the average of uh, average over all those training average over all those different models, right?
So
And
yeah,
different
so when
models.
we are doing averaging, so it is kind of moving towards the correct side. That is why variance will become
It is
low.
reducing variance, right? It
Yes.
reduces variance. Always make sure that whatever estimators you are using in bagging, it must have high variances. Otherwise, the bagging will be insignificant.
Okay, kind of which model to select, then that kind of situation.
Yes, yes. So mostly decision trees with the maximum possible length are preferred for bagging. Okay. So there's one famous algorithm for bagging, which is called random forest. So in the random forest, we use it's the bagging algorithm. So the algorithm goes in the same manner. We create m different training data set, m different bags. Over those m bags, we train m different training data decision trees. So these decision trees are of maximum length. But one important step here is that for creating any decision tree, we have to make sure that to split any node, we have to take some subset of the random subset of the features, not all the features you have to consider. You have
So
to
like
consider
there are n data points with each having m features. So from m features, we are randomly
randomly
selecting
selecting
some,
to
say,
to
small m
split any
features.
node within the decision tree. You choose some random subset of features, and how many you choose, you define it previously. Okay, so let's say if there are there are d features, then root over d features are generally taken as number of random features to consider for splitting any node. Okay, so this is the only
So is
difference.
bagging applied
And
on number of data sets as well, or only on the feature?
sorry.
In this random forest, we
Mhm.
select random number of subset of features. So
Yeah.
if the bagging is applied on the data points as well or not?
No, no. Bootstrap dataset is always created for random forest. Okay, so it's a bagging algorithm. So algorithm goes in the same manner. You create m bags, different m bags, train m different decision trees, and then make predictions depending upon taking over averages, right? So here on the only difference here is that you have to make sure that while you splitting those nodes, you have to take random subsets of the features, not all the features. Okay, and why we
Right.
do that? Just to make sure that all those
So
trees that
this
we are
this
training.
uh, this random subset of features is fixed at the beginning of the
Yeah,
model
number of
training,
how
and it
many
is
features you are
same in
training.
the same iterator, all the iterations.
Yes, yes, it's so same all iterations. Okay, generally it is set like that. Okay, so why actually we need different we need subset of features, just because just to make sure that those estimator that we are training, or say dot decision trees that we are training, are of wide varieties. If we consider all the data sets, then their structure may be similar, and for making predictions there will be same kind of output out of those m different estimators, and then aggregating those doesn't make any sense. So to make sure that we have different structures of those decision trees, we take some different subsets of features, not we don't consider all the features. Okay, so this is all
Excuse
about
me, sir.
bagging and random forest. Yes.
Sir, just wanted a clarification. If we have a data point that we need to test here,
Mhm.
so we will send that data point to each of these trees in the random forest. Whatever result we get, we will aggregate it and get the best result.
Aggregate means we take majority as the final prediction.
All right, sir. Okay, sir, understood. So every tree will get the data point and it will
Yes,
label it accordingly and we will take the majority.
majority. Yes.
Okay, sir. Thank you, sir.
Okay. So any other doubt in random forest? Okay, if not, we can move to the next part in boosting. So remember here, we are trained in the bagging, the training process go in parallel, right? Because those estimators are independent to each other. The training process go in parallel. All those different estimators we can train in parallel. But in the boosting, what we do, we start with some weak learner and then boost its performance. We check its performance and try to boost its performance in the next estimator. So here we train the estimators in the iterative manner. We start with the weak learner. So what is a weak learner? Weak learner is one whose performance is slightly better than a random model. Random model means that we just randomly making the predictions. For in that case, the error on an average error may be 0.5. So the weak learner are ones whose error is just less than 0.5. Okay, so we start with a weak learner. So stumps are the examples of weak learner. Stumps are ones are decision trees whose length is one, or say whose decision tree is with only one split. Okay, so in the boosting we use in AdaBoost we use, okay, generally in AdaBoost we start with the weak learner. Okay, and then we boost its performance. So how to do that? So there's this algorithm for that. We first we have a training data set. We randomly select one data set uniformly, create one training data set. It means that let's say you have 100 data points and you create a training data set of 100 points, and uh, with the uh, with the sampling from the original data set, but the uniformly sampling, that is each and every point have equal weightage to be selected or equal probability to be selected in that training data set. Now we train a stump over there. Stump means a decision tree. We train a stump over there and check its performance. So performance is actually defined as 1 by 2 log 1 minus error upon error, where error is proportion of the misclassified point. So for that, remember, for making error we are taking original data set, right? We train the decision stump over the bag that we have created. Now we are making predictions or over the original data set and finding the error, and
Sir,
then checking the
except this,
performance.
everywhere we follow the notion of base 2, right?
Yeah, log base 2.
Yeah,
No,
except
here
here.
it is log base e.
Yeah, yeah.
Log.
Okay.
Okay.
Okay, sir. Thanks.
Okay. Now, once we check the performance of the model, then we train the next model in such a way its performance becomes better. So how to do that? Then for doing that, we create a new data set, but now we take the different weightage to be selected in the new bag. So we make sure that the incorrectly classified point takes higher weightage to be selected in the next bag, and the points which are correctly classified takes the low weightage to be selected in the next bag. Okay, so for that we okay, so we are missing out some slides here. So for the incorrectly classified points, let's say the initial bit by 1 by n are the total number of data points. So in the very first bag, all have the equal weight is 1 by n. But in the next bag, what happen if the point is incorrectly classified? We increase the weights by e raised to power alpha. So then weight will be 1 by n e raised to power alpha for incorrectly classified point, and for correctly classified point, weight will become 1 by n e raised to power minus alpha. Right. So that's how we assign the weights for different data points for the training, and we just make sure that those becomes a probability distribution. So we make sure that the sum over all those weights are equal to 1. So we divide it by the summation over all the weights to make sure that it's it's a valid probability distribution, and then over that probability distribution we create the new data set. It means that the now selecting a data points have the different probabilities than random. Okay, now we create a new bag. Over those new bag we again create a decision stump and again check the performance. Based on that performance, we again create we again assign new weights to the training data set, and then keep on doing in the similar manner. Okay, so this is AdaBoost algorithm. At some point of iterations, that AdaBoost algorithm may give you the zero training error, right? So this is good part of the AWS algorithm. At some point of time, point of iterations, it training error becomes zero, and even training error becomes zero, the test error doesn't go higher. Okay, so this is the beauty of the AWS algorithm, and we didn't cover the mathematical part of that. Just think about just focus on the steps that are followed in the AWS algorithm. So remember, we start with a bag. We train a decision system that we check the performance over there, and then we assign different weights to the training example to create the new bags, and then keep on repeating the same procedure. Okay, so only difference in bagging and boosting is that bagging takes the overfitting model, but in the case of boosting, we takes weak learners like underfitting models like decision systems. Okay. And in the bagging, all the training can go in parallel, but in the boosting, the training process go in the iterative manner. That is, we train first model, then checking performance, and then we, based on that performance, we train the next model.
Sir, can you just solve that graded assignment 11 question 5 in this regard? I have just some small doubt over there.
Okay, give me 1
If you
minute.
can solve that, then that will help us.
Okay, just give me 1 minute. Let me check. Let me open that portal. Question number 5, right?
Yeah.
Okay, I give you the idea. I'm not gonna do the calculation here. So, okay, so this is your question. There it is said that this is your data set, and for
Could you
AWS,
share the screen?
yeah, I've shared the screen. Is it not visible?
Yeah, now it is visible.
Okay, so here in this question, it is you have been given this data set, and it is mentioned that you have to split to create the decision system. You have to split the data set according to this question: x2 is less than 4 or not. So what will be your decision system? So you have to check whether x2 is less than 4 or not. So all these 2 points go into the left node, left child, and these 3 will go into the right child, right? So what will be the prediction in the left node? Majority class,
No.
right?
3 will go to the left and last 2 will go to the right.
No, it's strictly less than 4. So x2 less than 4 will go to the left child, and x2 greater than or equal to 4 will go to the right child.
Correct.
Okay, so these 2 will go into the left child. Okay, so in that case, majority will be the final prediction. So 0, 0 are there, so it is a pure node. Prediction will be 0. But in the right node, predictions will be what? 1, because majority is of 1, right? So how many? What is the error for that decision system? Only 1 is
Fourth point.
misclassified. So 1 by 5 is the 1 by 5 will be the error. So what will be the what is asking? What is the value of alpha node? This is 1 by 2 ln 1 minus error by error, right? So 1 minus 1 by 5 upon 1 by 5. So it will become 4. 1 by 2 log 2.
No,
Log
sir,
4.
you just repeat the calculation of the error part. How do you calculate that?
So in the left node, these 2 are the training examples, right?
Correct.
And what is the predictions for these 2 points?
These 2 points are less than 2. So correct. Right.
Correctly classified, because the true level are actually the predicted levels. But if you go for the right child, what will be the predictions there?
Prediction is that is wrongly classified.
Predictions, what will be the prediction in the right child? There are 2 points belonging to class 1 and 1 point belonging to class 0.
So 1.
1 will be predictions, right? So, and this point has the true level as 0. So this point will be misclassified there.
Okay.
Right? So only 1 point is got misclassified. So the error will be 1 by 5.
Okay.
Okay. So I think we are running out of time. We can move to the week 12, and then we can take the questions after that.
Okay, sir.
Okay.
Yeah, okay, Nitin.
Okay.
Okay, is my screen visible? Am I audible and my screen is visible?
Yes. Yes, ma'am.
Okay. All right, so let's go over week 12. So let's first talk about different classification loss functions, right? Let's say this is the data that is given to us, and yi can be a value between value amongst +1 or -1. What is the motive of classification? What is the motive? That for +1, the predicted class should be +1. For -1, the predicted class should be -1. And if it is not so, For example, for +1, we are getting a -1. For -1, we are getting a +1. So we add up an error. So this is the most intuitive way to see how much error a particular model is making, a particular classification model is making, right? So if +1 is being predicted as -1, you add up an error of 1. Similarly, if let's say -1 is being predicted as +1, you add up, and so on and so forth. This is what will be your error, right? This is the total error that you get. Now, if you have to visually represent it, how would you do that? Let's see. But whatever we have done here, let me put it in the form of an equation. So indicator function is what you can use. So if H is the model, H of xi will give you the value given by the model. You have to compare this H of xi with y. You have to compare these two things. In case of H of xi is equal to yi, there is no error. But in case it is not equal to yi, then you add up an error, right? That's what we did. So that's why you can represent this loss by using this indicator function. This is also called 0-1 loss. This is the most intuitive explanation for recording the amount of error that is happening through a classification model. Now, if you have to visually see how it would look like, so this is an error for one data point. Similarly, if you put a summation, you can see the error, total error made by the model. Now, we'll focus on one data point for now. So this is your H of xi. So in case of a 0-1 loss, so there'll be some g of x that will be given by the model, and you will see the sign of g of x. So let's say your H of xi. So there was some confusion that you people had regarding this very representation. So g of x is given by the model, and then we look at the sign of g of x, and that is what is predicted by the model as the label, right? So please note what gx and hx are. Gx is given by the model, and we look at the sign, and then we compare with yi. So that's the terminology. Now, this very loss can be written in an alternate form, and that is, this is your g of x. You multiply it with y. If there is an error, this value will be less than 0. If there is no error, then g of x into y will be greater than 0, greater than equal to 0, right? Why we can do like this? See, y can be either +1 or -1, right? If gx is positive, right, and y is positive, this whole thing will be positive. This case. If gx is positive and y is positive, then this multiplication will be positive, and hence there is no error, right? This is the case when there is no error. The other case could be this y is negative, g of x is negative, then the multiplication will be positive, hence it will be greater than equal to 0. So this is the case when there is no error, right? And when error happens, then what will be that scenario? Let's say y is positive and gx is negative. So the whole thing will be negative. On the other hand, this is negative and this is positive, and the multiplication is negative. So this is an error scenario. So if you have to plot it, you can have gx into y on the x-axis, and on the y-axis we have the loss. As we see, when gx into y is greater than equal to 0, which is this part, there is no loss, right? Because this is a scenario where there is no loss. On the other hand, when gx into y is less than 0, then there is a loss, and that is 1 in case of 0-1 loss, right? So this is the representation of 0-1 loss, right? Now, in linear regression, what was the loss? Squared loss, right? And it is a differentiable function. It's a nice convex function, so we can apply something like gradient descent, right? So we were sorted there. But here in classification, this is the kind of loss function that we are getting, and we know that this is actually not continuous as well, and of course not convex. So we cannot apply something like gradient descent or any other optimization technique on this 0-1 loss, right? That's the problem in classification, which was not there in regression. So one might wonder, can we apply a regression loss here in classification also, since we know that we were doing decently well in regression by using something like squared loss? Can we do that here as well, right? What do we mean by that? So if we apply squared loss in case of classification, so it will be something like gx minus y square. For one data point we are talking about, it will be like this, right? Now, if you see, this term is actually equivalent to g of x into y minus 1 square. These two terms are actually same, right? You can actually see, you can expand this, they will both come out to be equal. Now, if you have to plot this here, let's see how it will look like. So when when let's say gx is positive and y is positive, gx into y will be positive, right? This whole thing will have a huge value. So let's take a few cases one by one. Let's say when gx into y is equal to 1, what will happen? The loss will be 0, right? Let's say over here, this is 1. When gx into y is equal to 1, the loss will be 0, right? Loss will be this. And when gx into y is equal to 0, this loss will be 1. So we are here, right? And when gx into y is some positive value, this whole thing will be a huge loss. In this particular region, this will be a huge loss. So if you see this will come out to be something like this, squared loss, something like this, right? Now you see it is a convex function, but this region, if you notice, this is the region where actually there should not be any error. Why? Because let's say gx is some positive value and y is, we know it is plus 1. So this multiplication becomes a positive value, some value greater than 0. So there is no error. As per classification, there is no error happening in this particular case. But squared loss will give a huge value, which is this region. So this very region, this region, there's a whole, this should give you a 0 error, but squared loss is giving you a huge error. So we see that squared error is not an appropriate loss to be used in case of classification. Okay, so let's leave it at that. Now, there are several classification techniques, and every technique is trying to come up with a loss function, and that's how we are sort of managing this 0-1 loss. So like I told you, that 0-1 loss is the most intuitive way to look at the error produced by a classification model, but we also know that it is not appropriate to be I mean, we cannot take a gradient of this, right? We cannot use it in our computations. So we try to come up with different loss functions. These different loss functions are actually called surrogate loss functions. Surrogate loss functions, right? For example, we know there is SVM, and we know there is a logistic regression, and we know there is perceptron, and there is boosting. All these techniques are used for classification, right? So all these techniques come up with some loss function where we try to achieve a similar effect that is achieved by the 0-1 loss. Okay, so let's take them one by one. For example, let's look at SVM. In SVM, we use hinge loss, right? So hinge loss is max of 0, max of 0 and 1 minus W transpose Xi Yi, right? This is your hinge loss, which is used in SVM, right? So if you look at hinge loss, so this is W transpose Xi Yi, this is actually same as 1 minus Gxy we are taking, right? So we can write it in those terms, right? Now, if you have to plot this, how would it look like? Max of 0, 1 minus gxy. When gxy is equal to 1, this whole thing will be 0 and the loss will be 0, right? Which means at this point the loss will be 0. Now when gxy is equal to 1, what will happen? When this is when this is 0, what will happen? When this is 0, this is 1 and max is 1. So when this is 0, the loss will be this much, right? And when gxy is some value greater than 1, let's see what happens. When gxy is some value greater than 1, this whole thing will be negative and the max will be 0, which means the loss will be 0. This is how it looks like. So this part we are actually matching 0, 1 loss. So good so far. So far so good. We can see the rest of the region. This one we are sorted. When gxy is a huge negative value, what will happen? Gxy is a huge negative value. So this is positive. So this will be the value that we'll get. I mean, this will be the max value, right? So this is a kind of, this is straight line, okay? So this is a kind of, loss function that we get. And we see that this is convex, right? So hinge loss in particular is trying to model the 0, 1 loss in a different manner, right? Of course, when SVM uses it, there's another term associated which is used for regularization. This is also there, but this is hinge loss and this is a regularization term. So as you can see that hinge loss is also trying to model the 0, 1 loss, but using a convex function, right? So that's about SVM. Similarly, if you look at, let's say, logistic regression, what is the loss that we use in logistic regression? What is the loss? We just now did, right? Some 2 hours back we did this. We are trying to maximize the, sorry?
No, I'm just trying to say the loss function.
Okay, so the loss function that we use is actually log loss. So I had told you some 1 hour back that we are trying to maximize the likelihood, which means we are trying to maximize. So this is maximization. We're trying to maximize. This is sigmoid, and this is W transpose X. In case of when the class is positive, +1, we use this, and when the class is negative, we use this term, and this is 1 minus yi. So this is what we are trying to maximize in case of logistic regression. Now you can convert it into a minimization problem as well. So first you can take a log of it. So when you take log, so this will become yi, then log of sigmoid of W transpose X, and 1 minus yi, and log of 1 minus sigmoid of W transpose X, right? Something like this you will get. This is again a maximization problem, but we are looking at loss here, right? So we have seen every technique's loss, which is something that should be minimized. So let's convert it into a minimization problem. So this is for all the data points. Sigmoid, the sigma is there. This is for all the data points. We are focusing on one data point, right? So let's remove this sigma so that we can focus on one data point, right? So we are converting this maximization problem to minimization problem. So I'll put a minus yi over there, and then rest remains the same. Minus 1 minus y you can write, or plus yi minus 1, and then rest remains the same. So what I want to tell you is this is a loss function that we are trying to minimize in logistic regression. And when yi is equal to 1, what happens? This whole term becomes 0, right? When yi is equal to 1, this whole term becomes 0. So we have this loss. Similarly, when yi is equal to 0, this whole thing becomes 0, and we have this term, right? So when you expand these two terms, you eventually get, so you can look at the derivation. I will not cover that derivation here. So what I want to tell you is that when you use classes to be 1 and 0, this loss function you use. And when you use classes to be +1 and -1, that's how we started off here, right? That's how we started off. So we're trying to convert this equation into an equation that can work when the classes are +1 and -1. Okay, and you can see the derivation in the class notes. So it will be 1 plus e to the minus w transpose xi yi, right? Or you can write it like this: log of 1 plus e to the minus gx yi, gx into y, right? So gx into y, I'm just removing the I term. So we got a similar expression in terms of gx into y is what I wanted to show you. So this is our loss function in case of logistic regression. Okay, and if you try to plot it, it's a log function. If you try to plot it over here, here you'll get something like this. Won't touch 0. Sorry, won't touch 0. So something like this you will get. So if you compare it with 0, 1 loss, it is trying to, get a smoother function of 0, 1 loss so that we can approximate it. Okay, and also it is convex. So that's what logistic regression is trying to do here. So basically, if you see, every classification problem is trying to come up with a loss function where we are trying to get a convex approximation of the 0, 1 loss. Okay, and that's why different approximations are there, and hence we have different techniques for classification as compared to regression, where we have mainly linear regression, and then we are regularizing that. Anyway, so different classification techniques can be seen as different variants. Now, one more thing I want you to focus on. If you look at Perceptron, there's an update rule that we use, which we saw that today. What is the update rule? Wt plus 1 is equal to right? So yeah, this is T is the iteration, right? So these are the weights. So new weight is equal to old weight plus x into y, right? We have seen that, x into y. Now, you might remember what is the update rule in gradient descent as well, right? What is that? What is that? Wt plus 1 is equal to Wt plus eta, then gradient of the loss function, right? That's what it is. Now, let's say we take eta to be 1, right? So essentially, if you compare these two things, we see that the perceptron is using some loss function whose gradient is xt into yt, x into y. Now, it's actually xi yi. I is the data point which we are looking at in the tth iteration. It's like that, right? So the point to note here is that the gradient of the loss function is being taken as x into y by perceptron. Okay. Now, if you look at the hinge loss, we have seen that, right? Maximum of 0, 0 and 1 minus gxy, 1 minus w transpose xy, 1 minus w transpose xy. We have seen this. We look at modified hinge loss so that we are able to compare all these functions. That's the reason why we are using modified hinge loss. So we are looking at 0 and minus w transpose xy. So this is the hinge loss. So this is just shifted by 1 unit. That's the hinge loss that we are looking at. Now, if you look at the gradient of this particular loss function with respect to w, right? Gradient of modified hinge loss, if you see with respect to w. So there'll be two cases, right? When w transpose x into y is less than 0, and the other case will be w transpose x into y is greater than 0. When this is less than 0 and this is less than 0, what will happen?
Minus xy.
When this is less than 0, this will be this whole thing will be positive, right? And the max of that will be this positive term, right? So which means the derivative will be derivative of this term with respect to w, which is minus xy, right? When w transpose x into y is greater than 0, which means this is greater, so this whole thing is negative, so max is 0. Okay, so these are the two cases of gradient. And we know one more thing, that we do, I mean, if you look at the hinge loss, hinge loss, modified hinge loss, if you see something like this, modified hinge loss is this, and you will have to use a subgradient method at this point, because you cannot find the gradient at this point, right? At this corner point, you don't know the gradient, and the gradient at this line is minus xy, the gradient at this line is 0, and here you will have to use at this point, at this very point, you'll have to use subgradient method, right? Subgradient descent, which means you will have to, so there are several subgradients that are possible here, and you will use one of them. The slope will vary between 0 and minus xy. The subgradient that you will use, its slope will vary between 0 and minus xy. Now, getting back to where we started off about perceptron, we see that the perceptron has chosen a subgradient which is having slope minus xy, and that is why, well, one problem, there has to be minus here, right? This is gradient descent, we go in the negative direction, so this will be minus here. So perceptron chooses the subgradient which is minus xy, and put a minus there. So if you compare these two, then the gradient of loss is minus xy. Okay, minus minus plus, that's how we get a plus in perceptron update rule. So all we are just doing is we are comparing perceptron with the gradient descent rule, and we see that it is actually, so perceptron applies on each data point one by one. That's another point to note. On the other hand, something like gradient descent applies on all the data points. But if you see stochastic gradient descent applies on each data point one by one, right? It chooses one data point at a time. So perceptron
No, few data points at a time.
Actually, stochastic, okay, there's a confusion there in the sense as to what is covered in lectures. So, gradient descent takes all the data points, right? Mini batch gradient descent takes a subset of the data points. Stochastic gradient descent takes one data point. But I think, in the lecture, stochastic gradient descent has been stated to be, covering a subset of data points, right? So, okay,
Yes,
let's
ma'am.
stick to that.
Yeah, ma'am. Actually, epoch, what they are saying that.
Yeah, okay, fine. You can you can stick to that. But okay, getting back to perceptron, it looks at each data point one by one, right? So perceptron can be looked at similar to a hinge loss. Okay, perceptron can be seen as a technique which uses a variant of hinge loss. Okay, so that's how we can see the similarity between different loss functions, and we can see that all the loss functions in different classification techniques are trying to sort of approximate the 0-1 loss in the attempt to get a loss function which is convex. Okay, because 0-1 loss is not convex. Okay, so that was some discussion on different loss functions in classification. Now, next is neural networks, which we have.
So before moving on to neural network, could you please go back to that place where you were discussing about y equal to 1, 0 and y equal to plus 1, minus 1? I mean, I didn't quite catch what.
Sorry, which one?
Here only, you said while discussing the loss function for logistic regression, y can be either 1, 0 or plus 1, minus 1.
Yeah.
So it changes accordingly.
Yeah. Okay, you. Sorry, I should show you the derivation. So
no, a derivation
yeah, so
I can see in the lecture. So basis y equal to 1, 0 and plus 1, minus 1, the derivation changes. That is what you are saying.
Yeah. Why? So what is your question?
No, that is the only thing I wanted to confirm.
Yeah. So why we are doing this? Is this clear to you? Why did I say that if the classes are plus 1, minus 1, you use this function, loss function, and when the classes are 0 and 1, you should use this loss function?
Yeah,
why did you do
that you can clarify.
Yeah, so that's why I was bringing you to the derivation part here. So this part, if you see, I think I explained this, when, so Zi is same as Yi here, right? So when Zi is equal to 1, this whole thing becomes becomes 0, and the loss is this, and vice versa. Now, when you take up these both cases, When zi is 1, when zi is equal to 0, you expand this and you get this. Now focus on these two derivations. What we actually got was log 1 plus e to the minus w transpose xi, but we are putting in an extra yi over here. Okay, so we are trying to generalize, we are trying to come up with an equation which is kind of similar
In the same
for
form
both
in both the
cases.
cases.
Yeah, correct. So since yi is equal to plus 1, so zi is equal to 1 and y is equal to plus 1. And when zi is equal to 0, we are saying y is equal to minus 1, right? So here, there is no yi, but since y is equal to plus 1, there is no harm in putting a yi over here, isn't it?
Correct.
So that's what we are doing. Now getting back here, we didn't have a yi over here, but since zi is equal to 0 corresponds to y is equal to minus 1, if you put a yi over here, you put a minus here, right? So basically, if you replace yi by minus 1,
Yes, that is true.
you get this one. So now you get the same equation, right? Now these equations will work only when yi
Is 1
is
and minus
represented
1.
as plus 1 and minus 1, right? Okay. So that's why this differentiation, you can use any of these loss functions, will give the same value. Okay.
Okay. So why labels has to be plus and minus 1 to stick to this notation?
Yeah, no, the later one.
Yeah.
Yes. Okay. So neural networks, we'll see. So they have been briefly covered in the course. So let's look at them. So we've seen perceptron, right? So there are some inputs. So when I say x1, x2, x3, they are actually not different data points. They are different features of the same data point. So if I use f1, f2, f3, I don't know this, I'm changing the notation, but so far we were using x1 as data point 1, x2 as data point 2, right? That's what we were following. But
yes,
but right now what I'm trying to say is this, this is first feature of the, let's say we are talking about some data point xi. So this f1 is first feature of xi, f2 is first feature of second feature of xi, and so on. Now in perceptron, what we do, we take a linear combination of these. There is some weight vector, right? W transpose xi is what we come up with, right? And after that, what we do is we apply a sigmoid there. Sorry, in logistic regression, this is what we do, right? In logistic regression, this is what we do, right? We take the linear combination and then we apply sigmoid function, and that's how we get the probabilities, right? Now in neural networks, what happens? We have several of such units. Okay, we have several such units. So once again, the data will be the same. Sorry, yeah, this will be our data. Instead of one such unit, we'll have multiple units. Okay, and we call this one layer. Okay, this whole will be called one layer, and all these data inputs will go to all of these units and so on. Okay, like this, and these are called neurons. Okay, so what these neurons do, they take all these inputs and there's some weight vector. So all these edges will have some weight value. Okay, you can put that comfortably in some nice notation in form of a matrix, but let's skip that for now. So some weights are there. You can actually put them in a nice 2D form. Anyway, so these neurons first compute the linear combination of these inputs and then apply some activation function. These are the two things that every neuron does. This activation, there are several variety of activation functions that we can use. Now this is one layer. Okay, there could be several such layers and there could be several neurons in each layer, and finally there'll be one output layer. Okay, so each layer, what it does is, each neuron of each layer takes in the input produced by the previous neurons.
So
and
ma'am,
so on.
output layer will have only one neuron.
If it is a regression problem, output layer will have one neuron. Let's say it's a multi-class classification problem. In that case, it will be multiple neurons. I mean, the neurons will be equal to the number of classes in the data. Okay.
Madam, even the first layer, we should assume that they are the passive neurons.
Exactly.
In
I
case,
was about to go there. There was some doubt regarding this.
yes, ma'am.
So, yeah. So,
So if
I'll put
any
there.
list, like in graded question, if any list is given, so the list is first number has to be input layer and last number has to be output layer, and
Yes.
middle ones are the only the hidden layers, correct?
Yeah, right, right. So one more thing, see, each of these edges has some weight, which is a parameter to be computed. Apart from these, every neuron will have a bias value. Okay, every neuron also has a bias value. It's like this. So, so we'll get there how to compute the total number of parameters to be computed for a neural network. But one thing, we just discussed, the neurons at the input layer, they're actually, again, they're kind of passive neurons. They do not perform any linear combination. They do not apply any activation function. They simply do the job of passing the input to the subsequent layers. Okay, so that's how it is. So if there
So,
is
madam, in the test, if we get, we should assume that the first, whatever is the number, that is specifying the number of features. It is a passive layer.
Right, correct. Let me take you to that question. This one, right?
Yes, ma'am. This one.
So here, yeah, this is given. So the first, so this is first input layer, okay, and
no, ma'am, the wordings, the first statement, the wordings are talking about the number of neurons in different layers being represented in the list.
they're actually called neurons. It's just that they do not have any bias associated. They do not perform any linear combination. Okay, they do not have weight values associated before they pass the input. They simply pass the input. This is mentioned just to
hidden layer neurons and output layer neurons.
Yes, hidden layers and output layers will have weights and biases. Okay.
And first layer will be like input layer neuron. That is why it is stating that number of neurons in different layers.
Number of this. That's how it is generally stated. It is to tell how many inputs are there.
So
in
if the same thing has
network,
to be represented graphically, so first layer will it have any circles or the like one you have drawn? The first layer.
You can actually put circles, but I prefer doing it like this to avoid any confusion. People do that. That is also how it is done. But if you since you are confused about it, you can put it like this. Okay, that way you wouldn't get confused as to whether they would have bias or weights associated or activation functions associated or not. So if you have to convert it to a diagram, you can see that it will be like this. Yeah. So So one question that will be good to discuss: 3 hidden layers. I hope that is clear to everyone now.
And in case they give us a question with figure, even in that there will be no they will be given like x1, x2. There will be no circles for the inputs. The convention which will be followed for the exam.
Yeah, even if you see some diagram somewhere, you will not associate any bias with the input layer. Okay.
Yes. Okay.
Yeah.
No.
So the number of
what is asked, like in the exam, if the graph is given for the network, so the first layer, it will only be points, not smaller circles, correct?
So it should be, but even if, like I said, some people actually put circles here. This is also valid representation.
Okay, so if leftmost, if there is a graph which with leftmost circles, layer of leftmost circles and no edges coming into those circles, then that has to be interpreted as input layer.
Input layer, correct. Yeah. So if you have to compute how many parameters will need to be computed for this neural network, then you know that 5 neurons are here, 5 are here, 4, 3, 1, right? So 5 into 5. So like I said, it's a fully connected network. I mean, by default, it is fully connected, which means all these neurons will be connected to all the neurons in the next layer. So 5 into 5 will be the number of edges and hence the number of weights. Each edge will have a different weight. Similarly, over here, the same thing will happen. So 5 into 4, 4 into 3 here, 3 into 1 here. Now, apart from that, every neuron in output and hidden layer also has bias associated. Okay, so each neuron one bias. So how many neurons are there other than input layer? There are 5 here, and then 4 here, and then 3 here, then 1 here, right? So this is what is the total number of parameters. Is this clear?
Yes, ma'am. Number of
Yes,
bias
ma'am.
will be excluding the input layer as many neurons given. So that will be number of bias.
Actually, ma'am, there was a comment by you on one of the discourse posts where you had said the input layer contains only inputs and no neurons. That had confused a lot of us, and we answered
That
the graded
really,
assignment.
And we got
okay.
horrible marks in that graded
Yes,
assignment.
yes, that is the only assignment which is
Okay, don't
reflecting
worry
it.
about
It was
marks.
really
You got
bad
to learn,
marks.
that's
No,
fine.
that's all right. But
Do
the
better in
Yeah,
confusion.
we
exam.
learned it the hard way.
So that you will never forget it now, okay?
Yeah,
So
we
you
won't.
do well, you compensate in the final
Now,
exam.
if you
Okay?
give a question which is not fully connected network,
I
then
will not
again,
be fully connected because neural networks have not been that much covered in the course, so you won't get a question on that. Okay, they're actually briefly introduced here, so we won't get into much details about how to find these parameters and all. Okay, all
Ma'am,
right.
question number 5, if you can just explain in the same thing.
Which one? Graded 5.
Yeah, 5. Yeah.
This one
Yes,
or this one?
yes. No, question 5.
This only, right?
Hmm.
Yeah. What will be an appropriate activation function for the output layer? So we are looking at this scenario only. There is only one neuron at the output layer, and also it is given that it's a regression task, right? So a regression task in regression, the activation function that is used is linear, right? So sorry, we are asking for output layer only, right? Yeah. So in the output layer, if it is a multi-class classification problem, then we use we are asking at output layer, right? So we compute, we actually use softmax in output layer if it is a multi-class classification problem. So yeah, there was a confusion on that also because that was not in detail covered in the lectures. But anyway, so
Why this is not option C is correct here? Because I didn't find much
what does
difference
ReLU do?
between the linear and
What does ReLU do?
ReLU, because ReLU only take the actual value
No, ReLU converts the negative
instead
value
of.
into positive value, right? ReLU converts the negative value to zero value, isn't it? ReLU converts the negative. How does ReLU look like?
A line down line and then linearly increasing.
So if there are negative values, they are converted to zero, and if there are positive values, they are kept as is, right? They are kept as it is. No change is made to the positive values. Negative are made zero, right? That's what you're
That
like.
means no change in value means this line is always at 45-degree angle.
Yes, 45, correct. Because there'll be no change. Yeah, so getting back to regression, in regression, do you apply any, getting back to linear regression, do you apply any activation of some sort?
No.
In logistic regression, do you apply any activation?
Sigmoid,
right? In regression, you don't apply any activation. It's just the linear regression is just a linear combination of inputs, right? Just weights are applied. So that's why in regression, we just use linear activation, which is nothing but it simply passes. It is also called identity. It simply passes whatever is given to it. Okay, since we know it is a regression problem and there's only one, and of course there's only one output, one neuron at the output layer. So the activation function will be linear. Okay.
If it is a multi-class classification, then what would be
softmax.
the option for
Softmax.
the appropriate active? Then as you said, the softmax will come into the
Softmax,
picture.
right? So e to the xi divided by summation of e to the xi. I goes from 1 to d, where d are the number of classes. Okay. So the result is that all the probabilities are, the sum of all the probabilities is 1, right? That's what we want, right? If there are, let's say, 3 classes, we should get 3 values, and the sum of them should be 1, so that we can choose whichever is the highest. We'll predict that label. That's what we want in a multi-class classification, right? That's why softmax will be used.
Okay.
Okay, so I'll just quickly go over. I think we're almost done. I'll quickly go over this. If there is any doubt, you can please ask me.
Question 6, ma'am, in the same
Graded?
paper.
Graded?
Yeah. Why is this necessary to be always in 45-degree angle?
Yeah, I just now told, no. So what is ReLU? If the input is 10, what will be the output?
10.
If the input is 20, what will be the output?
Acha, that is why.
Right, no? Okay. All right. So different activation functions we have seen. Sigmoid, ReLU are generally used. And
One question regarding this, ma'am. In the graded assignment, the linear, was that covered? I'm sorry, I lost my connection.
No problem. Which one?
Which classifier to, which
activation
function to choose for?
Yeah. So we covered this. So here we know that it's a regression problem, right? We are given that it's a regression task. In regression, we use linear activation function. That's all. Why? Because in linear regression we don't apply any activation. It's simply the linear combination of inputs, right? We don't alter it at the end. So that's what we want here in case of regression also. So linear is the activation function that we use, also called identity. Yeah.
So ReLU is primarily for, I suppose, for
hidden
classification.
layers.
Okay.
Yeah, ma'am. ReLU can be understood. Yeah, ma'am. ReLU can be understood as just opposite of what hinge loss was. There, it was for all the positive values, it was going to 0, and here for all negative values, it is.
Hinge was similarly opposite.
Yeah, but that was a loss. Here it is input.
That was loss, correct. That's the difference. That was loss. That is also modified hinge, not the hinge that we use.
We took one out of it.
Yeah, we took one out.
Okay.
So
has the range any impact on our choice of activation function? Like sigmoid has 0 to 1.
Range of
range of the function, activation function. Like sigmoid would output 0 to 1.
Sigmoid outputs between 0 and 1.
0 to 1.
And then there's
ReLU
another
between
one,
0 to infinity.
TANH, ReLU between 0 to infinity. Yeah. So ReLU has ReLU is prone to overfitting actually. So we will not get into the details of the comparison between these activation functions. There are few differences, like ReLU, not ReLU, TANH. If you see TANH and sigmoid, they have computation of e to the something, right? E to the power. So they are little slow as compared to ReLU. But then ReLU has some inclination towards overfitting. So few differences are there which you can consider if whenever you're actually working on neural networks. But for now, I mean, this much is sufficient for you to know. Okay, we are not actually. Yeah.
Sure. So, but we cannot generalize that sigmoid and TANH are preferred.
No,
for
we cannot generalize as such. In practice we actually try different functions, different activation functions. A few differences we do keep in mind. Of course, if it is classification, what should be appropriate? If it is regression, what should be appropriate? That we look at. But in general, you cannot always say that okay, we should always use this one in this particular scenario.
Okay. All right. Thank you.
Okay, so I think that's all. If there is any doubt, you may please ask me, or we'll close it then.
Well, how many questions we can expect in term number?
How many questions are there in the quiz 1, 2?
Around 16, madam.
Yeah, a little bit more here. It's
we are given more time also, no?
Yeah,
we are given more time.
You have half an hour extra and a few extra questions. Yeah.
Okay, what kind of weightage we can expect along weeks?
Yeah, I told, right? First 8 will be having 40% weightage. Last 4 will be having 60% weightage roughly.
Okay, thank you.
Okay. All right, I think that's all. All the best to you for your exam. I
Thank
hope
you,
you
ma'am.
practice well.
Thank you.
Yeah.
Thank you, ma'am.
Thank you,
All
ma'am.
right, practice all the questions. You have sufficient material. Don't worry. All the best. Bye.
Okay, thank you.
Thank you, ma'am.
Thank you, ma'am.